Something moved in the darkness, and the earth trembled. Not a god, not a storm, but something far older, far stranger. Long before humans walked the earth, titans ruled it. With jaws like bone-crushing traps and eyes that pierced through time, dinosaurs weren't just animals. They were living myths, forged by evolution and crowned by chaos. Then they vanished, in the blink of a cosmic eye. Now, fossils whisper their secrets. Scientists dig through stone and silence, uncovering claws longer than swords and creatures with feathers, not scales. Once seen as sluggish beasts, they're now revealed as swift, complex, and terrifyingly intelligent. Dinosaurs were a diverse group of reptiles that dominated Earth for over 160 million years. These fascinating creatures first appeared during the Triassic period, about 230 million years ago, and ruled the planet until their extinction at the end of the Cretaceous period, roughly 66 million years ago. Scientifically, dinosaurs are defined by several key anatomical features. They possessed upright limbs positioned directly beneath their bodies, unlike the sprawling limbs of many other reptiles. This adaptation allowed for more efficient movement and supported their often massive body sizes. Dinosaurs also had distinctive hip structures, with either lizard-like or bird-like pelvic arrangements. Another crucial characteristic of dinosaurs was the presence of a hole in their skull between the eye socket and nostril, known as the antorbital fenestra. This feature is not found in other reptile groups and serves as a defining trait for dinosaurs. Additionally, many dinosaurs had hollow bones, similar to modern birds, which are their closest living relatives. It is important to note that not all prehistoric reptiles were dinosaurs. Flying pterosaurs and marine reptiles, like plesiosaurs, while often associated with dinosaurs, belong to separate reptile groups. The term dinosaur specifically refers to the land-dwelling reptiles that shared the unique anatomical features mentioned earlier, showcasing the incredible diversity of prehistoric life on Earth. Dinosaurs first emerged on our planet during the Triassic period, approximately 230 million years ago. This era marked a significant turning point in Earth's history as the supercontinent Pangaea began to break apart and new ecosystems formed. The earliest dinosaurs were small, agile creatures, quite different from the massive beasts we often imagine. These pioneers shared the landscape with other reptiles, early mammals, and a variety of plant life. Over time, dinosaurs diversified and adapted to fill numerous ecological niches. Their rise to dominance was not immediate. It took millions of years for dinosaurs to become the Earth's predominant land animals. This ascent was partly due to their ability to adapt to changing environments and outcompete other reptilian groups. The appearance of dinosaurs set the stage for one of the most fascinating chapters in our planet's biological history. Their emergence and subsequent evolution would shape Earth's ecosystems for over 160 million years, leaving an indelible mark on our world that we continue to uncover and study today. Dinosaurs reigned supreme on Earth for an astoundingly long period, spanning approximately 165 million years. This vast time frame, known as the Mesozoic era, encompasses three distinct periods: the Triassic, Jurassic, and Cretaceous. Their dominance began around 235 million years ago during the Triassic period, when the first dinosaurs evolved from earlier reptilian ancestors. Throughout their long reign, dinosaurs diversified into an incredible array of species, from the towering sauropods that shook the Earth with each step to the agile, feathered theropods that would eventually give rise to modern birds. They adapted to various environments, from lush tropical forests to arid deserts and even polar regions. The dinosaurs' rule came to an abrupt end about 66 million years ago at the close of the Cretaceous period. A catastrophic event, likely an asteroid impact, triggered a mass extinction that wiped out approximately 75% of all plant and animal species on Earth, including most dinosaurs. This event marked the end of the Mesozoic era and paved the way for the rise of mammals. To put the dinosaurs' lengthy dominance into perspective, modern humans have only existed for about 300,000 years, a mere fraction of the time dinosaurs ruled the planet. The dinosaurs' extended reign allowed for remarkable evolutionary adaptations and diverse ecosystems that continue to fascinate scientists and capture our imagination today. The Mesozoic era, often called the Age of Reptiles, is divided into three distinct periods. First came the Triassic period, which began about 252 million years ago. This was a time of recovery after the devastating Permian extinction, with the emergence of the first dinosaurs and early mammals. Following the Triassic was the Jurassic period, starting approximately 201 million years ago. This period saw the dominance of large dinosaurs and the evolution of the first birds. The Jurassic world was characterized by lush vegetation and warm, humid climates. The final period of the Mesozoic era was the Cretaceous, beginning around 145 million years ago. During this time, flowering plants appeared and diversified rapidly. The Cretaceous ended dramatically about 66 million years ago with a mass extinction event that wiped out the non-avian dinosaurs and many other species. Each of these periods brought significant changes to Earth's flora and fauna, shaping the evolution of life as we know it today. The Mesozoic era as a whole lasted for about 186 million years, witnessing the rise and fall of some of the most iconic creatures in Earth's history. Scientists employ several sophisticated methods to determine the age of dinosaur fossils. One primary technique is radiometric dating, which measures the decay of radioactive isotopes in the rocks surrounding the fossils. Potassium-40 argon dating is particularly useful for dinosaur fossils, as it can accurately measure ages up to billions of years old. This method relies on the known rate at which potassium-40 decays into argon-40. Another approach is biostratigraphy, where scientists analyze the layers of rock in which fossils are found. By studying the types of plants and animals preserved in each layer, researchers can estimate the relative age of the fossils. This method is based on the principle that certain species existed only during specific geological time periods. Magnetostratigraphy is yet another tool in the paleontologist's arsenal. This technique examines the magnetic properties of rocks, which change over time due to shifts in Earth's magnetic field. By comparing these magnetic signatures to known patterns of magnetic reversals throughout Earth's history, scientists can estimate when the rocks and the fossils within them were formed. Combining these methods with other geological and paleontological evidence allows scientists to build a comprehensive picture of when dinosaurs lived and died. This multifaceted approach helps ensure the most accurate dating possible, providing crucial insights into the age of dinosaur fossils and the prehistoric world they inhabited. Dinosaurs and pterosaurs were both remarkable creatures that lived during the Mesozoic era, but they had distinct characteristics that set them apart. Dinosaurs were primarily land-dwelling reptiles with a wide range of sizes and forms. They had legs positioned directly beneath their bodies, allowing for efficient movement on land. Some dinosaurs were massive herbivores like the long-necked sauropods, while others were fierce predators like the famous Tyrannosaurus rex. Pterosaurs, on the other hand, were flying reptiles adapted for life in the air. They had hollow bones and elongated forefingers that supported membranes, forming wings for flight. Unlike dinosaurs, pterosaurs had a more upright posture when on the ground, with legs attached to the sides of their bodies. This made them less agile on land, but exceptionally suited for aerial locomotion. Another key difference lies in their evolutionary lineage. Dinosaurs are more closely related to modern birds, with some dinosaur species eventually evolving into the birds we see today. Pterosaurs, despite their ability to fly, were not direct ancestors of birds and represented a separate branch of reptilian evolution. While both groups coexisted for millions of years, they occupied different ecological niches. Dinosaurs dominated terrestrial ecosystems, while pterosaurs ruled the skies, becoming the first vertebrates to achieve powered flight. This division allowed these fascinating creatures to thrive alongside each other, shaping the diverse and dynamic world of the Mesozoic era. The term dinosaur has a fascinating origin that dates back to the mid-19th century. It was coined by the English paleontologist Sir Richard Owen in 1842. Owen derived the word from two ancient Greek terms, dinos, meaning terrible or fearfully great, and sauros, meaning lizard or reptile. Owen introduced this term during a lecture at the British Association for the Advancement of Science. He used it to describe the fossils of large extinct reptiles that had been discovered in England. These creatures were unlike any modern animals, and Owen recognized them as a distinct group of reptiles that had dominated the Earth millions of years ago. The word dinosaur quickly caught on in scientific circles and popular culture. It provided a convenient label for these ancient creatures that were capturing the public imagination. Interestingly, when Owen first used the term, he was referring to only three genera, Megalosaurus, Iguanodon, and Hylaeosaurus. Today, we recognize hundreds of dinosaur genera, spanning a diverse range of shapes, sizes, and lifestyles. While our understanding of dinosaurs has evolved dramatically since Owen's time, his term has endured. It continues to evoke images of the awe-inspiring creatures that ruled our planet for over 160 million years, shaping the course of evolution and capturing our collective imagination. The discovery of the first dinosaur fossil is a tale that takes us back to the early 19th century. While people had been finding large bones for centuries, it wasn't until 1815 that the first scientifically recognized dinosaur fossil was described. This honor goes to William Buckland, an English paleontologist and geologist. Buckland examined a lower jaw and some other bones found in a quarry near Oxford, England. He named the creature Megalosaurus, meaning great lizard, and described it in a scientific paper published in 1824. This marked the beginning of formal dinosaur paleontology. However, it's important to note that Buckland didn't actually coin the term dinosaur. That distinction belongs to Sir Richard Owen, who introduced the word in 1842. Owen recognized that Megalosaurus and other recently discovered large reptile fossils represented a distinct group of animals, which he named Dinosauria. The story of dinosaur discovery didn't end there. Throughout the 19th century, more fossils were unearthed, leading to a boom in paleontology. This early period of discovery laid the groundwork for our modern understanding of these fascinating prehistoric creatures that once dominated our planet. Many people hold outdated or inaccurate ideas about dinosaurs, despite the wealth of scientific discoveries made in recent years. One persistent misconception is that all dinosaurs lived and died out at the same time. In reality, dinosaurs existed for over 160 million years, with different species evolving and going extinct throughout this vast period. Another common error is the belief that dinosaurs were all enormous creatures. While some species like the Argentinosaurus were indeed massive, many dinosaurs were no larger than modern-day chickens. The Compsognathus, for instance, was roughly the size of a turkey. Many also mistakenly think that dinosaurs were cold-blooded and slow-moving, like modern reptiles. However, current evidence suggests that many dinosaur species were warm-blooded and quite active, with some potentially capable of running at high speeds. The image of lumbering, sluggish beasts is largely inaccurate. Lastly, the notion that dinosaurs were evolutionary failures is far from the truth. These creatures dominated the Earth for millions of years, and their descendants, birds, continue to thrive today. In fact, the diversity and adaptability of dinosaurs demonstrate their remarkable evolutionary success. Scientists have identified and named over 1,000 different species of dinosaurs to date. However, this number continues to grow as paleontologists make new discoveries around the world. It's important to note that these known species likely represent only a fraction of the total number of dinosaur species that existed during their reign on Earth. The process of discovering and classifying dinosaur species is ongoing and complex. Researchers often work with incomplete fossil records, making it challenging to determine if a new find represents a truly distinct species or a variation of an already known dinosaur. As technology and scientific methods advance, our understanding of dinosaur diversity evolves, sometimes leading to reclassifications or the merging of previously separate species. Interestingly, the rate of dinosaur discoveries has accelerated in recent decades. This increase is due to improved fossil detection techniques, more researchers in the field, and exploration of previously unexamined regions. Some estimates suggest that a new dinosaur species is named approximately every 2 weeks, highlighting the dynamic nature of paleontological research. While the current count of known dinosaur species is impressive, it's likely just the tip of the iceberg. Many paleontologists believe that the total number of dinosaur species that ever lived could be in the tens of thousands. This vast diversity underscores the incredible success and adaptability of dinosaurs during their 160 million-year dominance of terrestrial ecosystems. The first scientifically recognized dinosaur species was Megalosaurus, a large carnivorous theropod that lived during the Middle Jurassic period, approximately 167 million years ago. This groundbreaking discovery was made in the early 19th century by British geologist William Buckland, who described the creature based on fossilized bones found in Oxfordshire, England. Megalosaurus, meaning great lizard, was initially thought to be a giant lizard-like creature, as the concept of dinosaurs was not yet established. The fossils Buckland studied included a lower jaw with teeth, vertebrae, and limb bones. These remains hinted at a formidable predator, estimated to be about 9 meters long and weighing around 1 ton. The identification of Megalosaurus marked the beginning of dinosaur paleontology, though at the time, the true nature and diversity of dinosaurs were not yet understood. It would take several more decades before the term dinosaur was coined by Sir Richard Owen in 1842, encompassing Megalosaurus and other newly discovered prehistoric reptiles. This initial discovery paved the way for future paleontological research, sparking scientific and public interest in these ancient creatures. As more fossils were unearthed and studied, our understanding of dinosaurs and their place in Earth's history began to take shape, leading to the rich field of dinosaur science we know today. Dinosaurs evolved from a group of reptiles called archosaurs over 200 million years ago during the Triassic period. These early ancestors were small, agile creatures that walked on 2 legs and had specialized ankle bones, setting them apart from other reptiles of the time. As the climate and environment changed, these proto-dinosaurs adapted, developing new features that would define the dinosaur lineage. One key development was the repositioning of their legs directly under their bodies, rather than splayed out to the sides like most reptiles. This allowed for more efficient movement and better support of their body weight. Over time, different dinosaur groups evolved distinct characteristics. Some became enormous plant eaters with long necks and tails, while others developed into fierce predators with sharp teeth and powerful jaws. The evolution of dinosaurs was not a single, straightforward process, but a complex branching of species over millions of years. Some groups, like the theropods, eventually gave rise to birds, showcasing the incredible diversity that emerged from those early archosaur ancestors. This evolutionary journey demonstrates nature's remarkable ability to produce a wide array of life forms from a common origin. As dinosaurs continued to evolve and diversify, they came to dominate terrestrial ecosystems for over 160 million years, shaping the world in ways that we can still observe in the fossil record today. Their evolutionary success story provides valuable insights into the processes of adaptation and speciation that drive life on Earth. Dinosaurs are classified into 2 major groups based on their hip structure: the Saurischia and the Ornithischia. The Saurischia, meaning lizard-hipped, includes the theropods and sauropods. Theropods were mostly carnivorous and walked on 2 legs, while sauropods were herbivorous with long necks and tails, walking on 4 legs. Famous examples of saurischians include Tyrannosaurus rex and Brachiosaurus. The Ornithischia, or bird-hipped dinosaurs, were all herbivores. This group includes well-known dinosaurs such as Triceratops, Stegosaurus, and the duck-billed hadrosaurs. Ornithischians had a more diverse range of body types and defensive adaptations compared to their Saurischian counterparts. Interestingly, despite the name bird-hipped, it was actually the Saurischian theropods that eventually evolved into modern birds. This unexpected evolutionary path highlights the complex and often surprising nature of dinosaur evolution and their relationship to present-day animals. Dinosaurs emerged during the Triassic period about 230 million years ago and quickly adapted to fill numerous ecological niches. Their diversification was a gradual process that unfolded over millions of years, driven by environmental changes and evolutionary pressures. During the early Jurassic period, dinosaurs began to dominate terrestrial ecosystems. This era saw the rise of long-necked sauropods and the first appearance of theropods, the group that would eventually lead to birds. As continents shifted and new habitats formed, dinosaurs evolved to exploit these opportunities, developing a wide range of body sizes, diets, and behaviors. The Cretaceous period marked the peak of dinosaur diversity. Flowering plants appeared, providing new food sources and habitats. This led to the evolution of specialized plant-eating dinosaurs like hadrosaurs and ceratopsians. Meanwhile, theropods diversified into various predatory forms, from small, agile hunters to massive carnivores like Tyrannosaurus rex. Throughout their reign, dinosaurs continuously adapted to changing climates and competition. Some groups became more specialized, while others maintained generalist traits. This ongoing process of diversification created the rich variety of dinosaur species that fascinate us today, from the towering brachiosaurs to the swift, feathered dromaeosaurs. Some of the largest dinosaur species ever to walk the earth were truly colossal creatures. The Argentinosaurus, a massive sauropod from South America, is often considered one of the biggest land animals in history. This enormous herbivore could reach lengths of up to 110 feet and may have weighed as much as 80 tons. Its long neck allowed it to browse vegetation at great heights, giving it access to food sources other dinosaurs couldn't reach. Another giant was the Dreadnoughtus, whose name means "fears nothing." This titanosaur, also discovered in Argentina, was nearly as large as Argentinosaurus. Scientists have found remarkably complete fossils of Dreadnoughtus, giving us a clearer picture of its immense size and structure. The Patagotitan, yet another South American giant, rivals these behemoths in size. It's estimated to have been up to 120 feet long and weighed around 70 tons. These measurements come from several well-preserved specimens, allowing paleontologists to make more accurate size estimates. While not as long as the sauropods, the Tyrannosaurus rex was one of the largest carnivorous dinosaurs. Growing up to 40 feet in length and weighing up to 9 tons, this fearsome predator was an apex hunter of its time. Its powerful jaws and sharp teeth made it a formidable carnivore, capable of crushing bone and tearing through tough dinosaur hide. Among the vast array of dinosaurs that once roamed our planet, some were truly tiny compared to their enormous cousins. The smallest known dinosaur was Compsognathus, a swift predator that lived during the late Jurassic period about 150 million years ago. This diminutive dinosaur was roughly the size of a chicken, measuring only 60 centimeters in length and weighing around 3 kilograms. Another contender for the title of smallest dinosaur is Anchiornis, a feathered creature that lived in what is now China during the late Jurassic period. It was slightly larger than Compsognathus, reaching lengths of about 30 to 40 centimeters and weighing up to 110 grams. Anchiornis is particularly notable for its well-preserved fossils, which have provided scientists with detailed information about its feather coloration. More recently, paleontologists discovered Oculodentavis kaungrai, initially thought to be a miniature dinosaur trapped in amber. This creature was incredibly small, with a skull measuring only 14 millimeters long. However, subsequent research has suggested that Oculudentavis might actually be a lizard rather than a dinosaur, highlighting the ongoing debates and revisions in paleontology. These tiny dinosaurs remind us that the prehistoric world was filled with diverse creatures of all sizes, not just the towering giants we often imagine. Their small stature likely allowed them to occupy unique ecological niches, demonstrating the remarkable adaptability of dinosaurs throughout their long reign on Earth. Dinosaurs thrived across diverse environments for over 160 million years, showcasing remarkable adaptability. Their success stemmed from evolving a wide array of physical features and behaviors to suit specific habitats and ecological niches. In arid regions, some dinosaurs developed efficient water conservation methods. The long-necked sauropods, for instance, had large, barrel-shaped bodies that could store water and food for extended periods. Their nostrils, positioned high on their heads, allowed them to breathe while partially submerged, accessing water in deeper areas. Dinosaurs in colder climates evolved insulation techniques. Some species, like the tyrannosaurids, likely had feather-like coverings to retain body heat. Others, such as the duck-billed hadrosaurs, had specialized nasal passages that warmed inhaled air before it reached their lungs, helping them survive in cooler environments. Coastal and marine-adapted dinosaurs developed unique features for aquatic life. Spinosaurus, with its long, crocodile-like snout and paddle-like tail, was well suited for swimming and fishing. Its dense bones helped with buoyancy control, allowing it to hunt effectively in water. These adaptations highlight the incredible diversity and resilience of dinosaurs across various ecosystems. Continental drift played a crucial role in shaping dinosaur evolution over millions of years. As the supercontinent Pangaea began to break apart about 230 million years ago, it created new environments and barriers that influenced dinosaur diversity and distribution. The gradual separation of landmasses led to the isolation of dinosaur populations, allowing them to evolve independently in different regions. This isolation resulted in the development of unique species adapted to their specific environments. For instance, the split between North America and Eurasia led to distinct dinosaur lineages on each continent. Climate changes associated with continental drift also impacted dinosaur evolution. As land masses moved, they experienced different weather patterns and temperatures, forcing dinosaurs to adapt or migrate. Some areas became more arid, while others turned lush and tropical, driving the evolution of various dinosaur body types and survival strategies. The movement of continents also created land bridges at different times, allowing dinosaurs to migrate between previously separated areas. This migration led to increased competition and further evolutionary adaptations as species from different regions interacted. Continental drift thus acted as a powerful force in shaping the incredible diversity of dinosaurs that existed throughout the Mesozoic era. The transformation of dinosaurs into birds is one of the most fascinating evolutionary journeys in Earth's history. This process began around 150 million years ago during the Jurassic period. Certain theropod dinosaurs, particularly those belonging to the group called maniraptors, started developing bird-like features over millions of years. These dinosaurs were already equipped with hollow bones and feathers, which were initially used for insulation and display. As time progressed, these features began to serve new purposes. The feathers gradually became more complex, developing into structures capable of providing lift. Meanwhile, the dinosaurs' bodies became smaller and lighter, adapting for a more airborne lifestyle. A key development was the transformation of forearms into wings. The wrist bones fused and the fingers reduced in number, creating a support structure for flight feathers. Simultaneously, these dinosaurs' tails shortened, eventually evolving into the compact tail feathers seen in modern birds. Their teeth were gradually replaced by beaks, which were lighter and more versatile for different diets. This evolutionary process didn't happen overnight. It took millions of years of gradual changes, with numerous intermediate species bridging the gap between dinosaurs and birds. With numerous intermediate species bridging the gap between dinosaurs and birds. The famous Archaeopteryx, discovered in Germany, represents one such transitional form, showcasing a mix of dinosaur and bird features. Through natural selection, the most flight-adapted individuals survived and passed on their genes, eventually leading to the diverse array of birds we see today. The connection between dinosaurs and birds is supported by a wealth of compelling evidence from various scientific fields. Fossil records provide crucial insights, revealing numerous dinosaur species with bird-like features. These include hollow bones, wishbones, and even feathers preserved in exquisite detail. The discovery of Archaeopteryx, often called a transitional fossil, showcases a creature with both dinosaur and bird characteristics, bridging the gap between these groups. Anatomical studies have revealed striking similarities in skeletal structure between certain dinosaurs and modern birds. The three-toed foot of many theropod dinosaurs closely resembles that of birds, and both groups share a unique wrist joint that allows for folding of the forelimbs. Additionally, microscopic analysis of fossilized bones shows similar growth patterns and internal structures in both dinosaurs and birds. Behavioral evidence also supports this connection. Some dinosaur species, such as Oviraptor, were found fossilized in brooding positions atop nests, a behavior characteristic of modern birds. Trace fossils of dinosaur nests and eggs bear remarkable resemblance to those of contemporary avian species. Furthermore, studies of dinosaur brain casts suggest that some species possessed the neural capacity for complex behaviors associated with birds, including flight and advanced visual processing. Genetic research has provided further confirmation of the dinosaur-bird link. Although dinosaur DNA is too degraded for direct analysis, studies of proteins extracted from dinosaur fossils have shown molecular similarities to those found in modern birds. This molecular evidence, combined with anatomical, behavioral, and fossil data, presents a robust case for the evolutionary relationship between dinosaurs and birds, supporting the theory that birds are, in fact, living dinosaurs. Dinosaurs possessed a remarkable array of skeletal features that set them apart from other reptiles. One of their most distinctive traits was their upright posture, with legs positioned directly beneath their bodies rather than splayed out to the sides. This allowed for more efficient movement and supported their often massive body weight. The dinosaur skull was highly diverse, varying greatly between species. Many had large eye sockets and nasal passages, while some developed elaborate crests or horns. Their jaws were often lined with powerful, replaceable teeth, perfectly adapted for their specific diets, whether herbivorous or carnivorous. The vertebral column of dinosaurs was another key feature, with some species having incredibly long necks or tails. These adaptations served various purposes, from reaching high vegetation to providing balance and defense. Many dinosaurs also developed specialized hip structures, such as the bird-like arrangement found in theropods, which later evolved into modern birds. Perhaps most famously, some dinosaur groups developed body armor, including plates, spikes, and osteoderms. These structures provided protection from predators and may have played a role in temperature regulation or display. The combination of these skeletal features allowed dinosaurs to dominate terrestrial ecosystems for over 160 million years, showcasing the incredible adaptability and diversity of these ancient reptiles. Dinosaur body plans varied dramatically across different species, reflecting their diverse lifestyles and evolutionary adaptations. The two main groups of dinosaurs, Saurischia and Ornithischians, had distinct hip structures that influenced their overall body shapes. Theropods, like Tyrannosaurus rex, were bipedal predators with powerful hind legs, sharp claws, and teeth designed for hunting. Their bodies were often streamlined, with relatively small forelimbs and long, counterbalancing tails. In contrast, sauropods such as Brachiosaurus had massive, pillar-like legs, extremely long necks, and small heads, allowing them to reach high vegetation. Ornithischian dinosaurs displayed a wide range of body plans. Ceratopsians like Triceratops had large, frilled heads with horns and beaks for defense and foraging. Stegosaurs featured rows of plates along their backs and spiked tails for protection. Ankylosaurs developed heavy armor plating and club-like tail weapons. Some dinosaurs evolved specialized features for their environments. Spinosaurus, for instance, had a sail-like structure on its back and adaptations for a semi-aquatic lifestyle. These varied body plans demonstrate the incredible diversity and adaptability of dinosaurs throughout their reign on Earth. Dinosaur hip structures were a defining feature that set them apart from other reptiles and played a crucial role in their classification. These ancient creatures exhibited two distinct hip configurations that became the basis for dividing them into major groups. The first type, known as the lizard-hipped structure, was characteristic of the Saurischian dinosaurs. This configuration featured a pubis bone that pointed forward, similar to modern lizards. Theropods like Tyrannosaurus rex and sauropods like Brachiosaurus belonged to this group. The second type, called the bird-hipped structure, was found in ornithischian dinosaurs. In this arrangement, the pubis bone pointed backward, parallel to the ischium. This hip structure is similar to that of modern birds, although birds evolved from theropod dinosaurs rather than ornithischians. Dinosaurs like Stegosaurus and Triceratops belonged to this group. These unique hip structures allowed dinosaurs to develop diverse body plans and locomotion styles, contributing to their success and dominance for over 160 million years. The hip configurations influenced how dinosaurs moved, balanced, and even reproduced, shaping their evolution and adaptation to various environments across the Mesozoic era. Dinosaur legs and feet underwent remarkable adaptations over millions of years, evolving to support various locomotion styles suited to different environments and lifestyles. The earliest dinosaurs were likely bipedal, walking on two legs, with three-toed feet similar to their ancestors. From this basic design, dinosaur limbs diversified into an array of specialized forms. Theropods, the group including carnivorous dinosaurs and modern birds, retained and refined bipedal locomotion. Their legs became increasingly bird-like, with a distinctive backward-pointing knee joint and digitigrade stance, walking on their toes. This design allowed for greater speed and agility, crucial for predatory lifestyles. Some theropods developed elongated metatarsals, forming a third leg segment that further enhanced their running abilities. Sauropods, the long-necked herbivores, evolved massive, column-like legs to support their enormous body weight. Their feet developed a more plantigrade posture, with weight distributed across the entire foot, including a fleshy pad. This adaptation allowed them to carry their immense bulk efficiently. Some sauropods also possessed claws on their feet, possibly for defense or for gaining traction on soft ground. Ornithischians, including horned and armored dinosaurs, showed perhaps the greatest diversity in leg structure. While some remained bipedal, others evolved quadrupedal stances. Ceratopsians developed legs that splayed outward, providing a stable platform for their heavy heads. Ankylosaurs had short, sturdy legs to support their armored bodies. Hadrosaurs retained the ability to move on 2 or 4 legs, with specialized wrist bones allowing them to walk efficiently on all fours when needed. Dinosaur crests and frills were remarkable features that served multiple purposes for these ancient creatures. These ornate structures, found on various species like Triceratops and Parasaurolophus, played crucial roles in their lives and interactions. One primary function of these elaborate headgear was visual communication. The crests and frills acted as striking displays that could be used to attract mates, intimidate rivals, or identify members of the same species. These structures often grew larger and more colorful as dinosaurs reached sexual maturity, suggesting their importance in courtship rituals. Additionally, these features likely served as thermoregulatory devices. The large surface area of crests and frills filled with blood vessels could help dinosaurs regulate their body temperature by absorbing or releasing heat as needed. This adaptation would have been particularly useful for maintaining optimal body temperature in varying climates. Scientists have also proposed that some crests may have functioned as resonating chambers, amplifying vocalizations and allowing dinosaurs to produce a wider range of sounds for communication. This theory is particularly relevant for hollow-crested species like Parasaurolophus, whose elaborate head ornaments might have acted as natural sound amplifiers. Dinosaur teeth were remarkably diverse, reflecting the wide range of diets these ancient creatures consumed. Carnivorous dinosaurs possess sharp, serrated teeth designed for tearing flesh and crushing bone. These teeth were often curved and dagger-like, allowing predators to grip and rip their prey effectively. The teeth of famous carnivores like Tyrannosaurus rex could grow up to 12 inches long, making them formidable weapons for hunting and feeding. In contrast, herbivorous dinosaurs had teeth adapted for grinding and chewing tough plant material. Many plant eaters, such as the long-necked sauropods, had simple, peg-like teeth, ideal for stripping leaves from branches. Others, like the duck-billed hadrosaurs, developed complex dental batteries, consisting of hundreds of teeth packed tightly together. These teeth would continuously grow and replace themselves, providing a constant grinding surface for breaking down fibrous vegetation. Some herbivores, including the horned ceratopsians like Triceratops, had beaks at the front of their mouths for snipping plants, followed by rows of leaf-shaped teeth for slicing and grinding. This combination allowed them to process a variety of plant materials efficiently. The stark differences in tooth structure between carnivores and herbivores provide valuable insights into the diverse ecological roles dinosaurs played in their ancient ecosystems. Interestingly, some dinosaurs developed specialized teeth for unique diets. Therizinosaurus, for example, had small, leaf-shaped teeth suggesting a herbivorous diet, despite being related to carnivorous theropods. This diversity in dental adaptations highlights the remarkable evolutionary paths dinosaurs took to exploit different food sources in their environments. Our understanding of dinosaur internal organs is limited, but paleontologists have made significant discoveries through careful analysis of fossilized remains. Soft tissues rarely survive the fossilization process. So much of what we know comes from studying bone structure, comparative anatomy with modern animals, and rare instances of preserved internal features. One of the most intriguing findings relates to dinosaur lungs. Evidence suggests that many dinosaurs, particularly theropods and sauropods, had a complex respiratory system similar to modern birds. This system likely included air sacs that extended into hollow bones, allowing for more efficient oxygen uptake and possibly contributing to their ability to grow to enormous sizes. Dinosaur hearts have also been a subject of study. While no complete heart has been found, analysis of chest cavities and rib cages indicates that dinosaurs probably had four-chambered hearts like modern birds and mammals. This adaptation would have supported their active lifestyles and high metabolic rates. Regarding digestive systems, fossilized stomach contents, known as coprolites, have provided insights into dinosaur diets and digestive processes. Some herbivorous dinosaurs, such as sauropods, likely had large, complex digestive tracts to process tough plant material. Carnivorous dinosaurs, on the other hand, probably had shorter, more acidic digestive systems optimized for processing meat. Dinosaur respiratory systems were remarkably efficient, setting them apart from many modern animals. These ancient creatures possessed a unique arrangement of air sacs and lungs that allowed for a continuous, unidirectional flow of oxygen-rich air through their bodies. This system was far more effective than the bidirectional breathing we see in mammals today. The dinosaur respiratory system consisted of multiple air sacs connected to highly specialized lungs. As a dinosaur inhaled, air would flow into posterior air sacs near the tail. During exhalation, this air would then move into the lungs, where gas exchange occurred. Simultaneously, the air that had already passed through the lungs during the previous breath cycle would be pushed out of the body through anterior air sacs near the head. This continuous flow ensured that oxygen-rich air was constantly moving through the lungs, maximizing oxygen extraction and enhancing overall respiratory efficiency. Such a system likely contributed to the impressive size and active lifestyles of many dinosaur species, allowing them to thrive in the oxygen-poor environments of the Mesozoic era. Interestingly, this respiratory system is not entirely lost to time. Modern birds, the living descendants of certain dinosaur lineages, have retained a similar breathing mechanism. This evolutionary legacy provides us with valuable insights into how dinosaurs might have breathed and helps explain their remarkable success over millions of years. Sauropod dinosaurs possess truly remarkable necks that set them apart from any other creatures in Earth's history. These colossal plant eaters, which included famous species like Brachiosaurus and Diplodocus, had necks of extraordinary length, often stretching up to 40 feet or more. This incredible feature allowed them to reach vegetation high in the treetops or sweep across vast areas to graze without moving their massive bodies. The secret to these elongated necks lay in their unique bone structure. Sauropod neck vertebrae were filled with air sacs, making them surprisingly lightweight despite their size. This adaptation enabled the dinosaurs to support and maneuver their lengthy necks without excessive strain. Additionally, these air sacs were connected to their respiratory system, enhancing their breathing efficiency and helping to regulate body temperature. Another fascinating aspect of sauropod necks was their impressive flexibility. Unlike mammals, which typically have only 7 neck vertebrae, sauropods could have up to 19 vertebrae in their necks. This increased number of joints provided them with a greater range of motion, allowing them to arc and bend their necks in ways that would be impossible for modern animals. The evolutionary advantage of these specialized necks was clear. They gave sauropods access to food sources that were out of reach for other herbivores. This adaptation played a crucial role in their success, allowing them to dominate terrestrial ecosystems for over 100 million years, becoming some of the largest land animals ever to walk the earth. Theropod arms underwent a fascinating evolutionary journey over millions of years. Starting with early theropods like Herrerasaurus, these dinosaurs had relatively long, grasping arms with sharp claws, useful for catching and holding prey. As theropods diversified, their arm structures changed dramatically to suit different lifestyles and hunting strategies. In some lineages, like the famous Tyrannosaurus rex, arms became drastically reduced. These powerful predators relied more on their massive skulls and powerful legs, rendering their arms less crucial for hunting. However, it is important to note that even these tiny arms were not entirely useless, potentially serving functions in mating displays or helping the animal rise from a prone position. Other theropod groups took arm evolution in the opposite direction. The ancestors of modern birds, like Deinonychus and Velociraptor, developed longer, more flexible arms with features that would eventually lead to flight. These arms bore feathers and had increased range of motion at the shoulder, setting the stage for the development of wings. Perhaps most intriguingly, some theropods like Therizinosaurus evolved massive, curved claws on elongated arms. These unusual appendages were likely used for pulling down branches to feed on vegetation, showcasing the diverse roles theropod arms could play beyond predation. This remarkable diversity in arm structure highlights the adaptability of theropods throughout their evolutionary history. Paleontologists have uncovered fascinating evidence of dinosaur social behavior through careful study of fossils and trace fossils. One of the most compelling pieces of evidence comes from dinosaur trackways, which show multiple sets of footprints moving in the same direction. These trackways suggest that some dinosaur species traveled in groups, possibly for protection or during migration. Fossilized nesting sites provide another window into dinosaur social structures. Discoveries of large nesting grounds, particularly for certain species of hadrosaurs and sauropods, indicate that these dinosaurs may have returned to the same nesting areas year after year. This behavior suggests a level of social organization and possibly even cooperative care for young. Bone beds, where multiple dinosaur skeletons are found together, offer additional clues about social behavior. Some of these sites contain the remains of numerous individuals of the same species, hinting at the possibility of herding behavior. For instance, ceratopsians like Centrosaurus have been found in massive bone beds, suggesting they may have lived and died in large groups. Certain dinosaur species also show evidence of pack-hunting behavior. Deinonychus, a small dromaeosaurid, has been found in association with much larger prey animals. This finding suggests that these agile predators may have worked together to bring down larger prey, much like modern wolves or lions do today. While interpreting behavior from fossils requires caution, these lines of evidence paint a picture of complex social interactions among many dinosaur species. Dinosaurs exhibited a range of intelligence levels, much like modern animals. Recent research suggests that some dinosaur species were more intelligent than previously thought. For instance, the Troodon, a small carnivorous dinosaur, had a large brain relative to its body size, comparable to that of modern birds. Many dinosaurs, particularly those in the theropod group, which includes species like Velociraptor and Tyrannosaurus rex, showed signs of complex behaviors. These behaviors included pack hunting, parental care, and the use of simple tools. Such activities require a certain level of problem-solving ability and social intelligence. However, it is important to note that brain size alone does not determine intelligence. The structure and complexity of the brain also play crucial roles. Some herbivorous dinosaurs, despite having smaller brains relative to their body size, likely possessed the necessary intelligence to navigate complex social structures within their herds. When compared to modern animals, the intelligence of many dinosaur species might be likened to that of present-day birds and reptiles. This comparison is particularly apt, given that birds are the living descendants of certain dinosaur lineages. While dinosaurs may not have reached the cognitive levels of the most intelligent modern mammals, they were far from the slow, dim-witted creatures once portrayed in popular culture. Fossilized footprints offer paleontologists a unique window into the daily lives and behaviors of dinosaurs, providing insights that fossilized bones alone cannot reveal. These preserved tracks, also known as trace fossils, allow scientists to reconstruct how dinosaurs moved, interacted, and even hunted. One of the most significant revelations from dinosaur footprints is evidence of herd behavior. Trackways showing multiple individuals of the same species moving in the same direction suggest that some dinosaurs, particularly herbivores like sauropods and hadrosaurs, traveled in groups. This behavior likely offered protection from predators and may have facilitated social interactions within the species. Footprint fossils also provide information about dinosaur locomotion and speed. By measuring the distance between footprints and analyzing their depth and shape, researchers can estimate how fast a dinosaur was moving and whether it was walking or running. This data helps create more accurate reconstructions of dinosaur movement and behavior. Furthermore, rare finds of predator and prey tracks in close proximity have given scientists insights into hunting strategies and predator-prey dynamics. These fossilized scenes of ancient dramas frozen in time help paint a more complete picture of the complex ecosystems that existed millions of years ago, bringing the prehistoric world to life in ways that capture the imagination and deepen our understanding of these fascinating creatures. Dinosaurs likely used a variety of methods to communicate with each other, much like modern animals do today. While we cannot observe their behavior directly, scientists have made educated guesses based on fossil evidence and comparisons with living relatives. Vocalizations were probably a key form of dinosaur communication. Some dinosaurs, particularly hadrosaurs, had elaborate hollow crests that might have functioned as resonating chambers for producing loud, low-frequency sounds. These calls could have been used for long-distance communication, perhaps to warn of predators or to attract mates. Visual displays also played a crucial role in dinosaur communication. Many species had colorful feathers, frills, or horns that could have been used in courtship rituals or to establish dominance within a group. Fossil evidence suggests that some dinosaurs, like Tyrannosaurus rex, had keen eyesight, indicating the importance of visual cues in their daily lives. Body language and physical displays were likely another important aspect of dinosaur communication. Behaviors such as head bobbing, tail wagging, or physical confrontations might have been used to convey intentions or establish social hierarchies within herds or packs. These non-vocal forms of communication would have been especially important for coordinating group activities or during hunting. Fossil evidence has revealed fascinating insights into parental care among dinosaurs. Paleontologists have uncovered numerous examples suggesting that many dinosaur species were attentive parents, much like modern birds, their living descendants. One of the most compelling pieces of evidence comes from nesting sites. Fossilized dinosaur nests have been found containing eggs arranged in careful patterns, indicating that adult dinosaurs actively prepared and maintained these nests. In some cases, adult dinosaur skeletons have been discovered in close proximity to these nests, suggesting they may have died while guarding their eggs. Trackways provide another line of evidence for parental care. Footprint fossils showing adult and juvenile dinosaurs walking side by side have been discovered, implying that parents guided and protected their young. This behavior is particularly evident in hadrosaurs, or duck-billed dinosaurs, where tracks of different-sized individuals moving together have been preserved. Perhaps the most direct evidence comes from fossilized stomach contents. In some oviraptor specimens, scientists have found eggshell fragments in the abdominal region. Rather than indicating that these dinosaurs ate their own eggs, researchers believe this suggests the adults were consuming eggshells to recycle calcium, a behavior seen in modern birds to strengthen their own eggshells for future clutches. This level of parental investment strongly suggests that dinosaurs were dedicated caregivers, challenging earlier notions of them as cold, uninvolved parents. Dinosaurs employed a variety of hunting strategies, each adapted to their specific physical characteristics and environments. Large predators like Tyrannosaurus rex relied on their immense size, powerful jaws, and sharp teeth to ambush and overpower their victims. These giants would likely have used short bursts of speed to close in on prey, delivering devastating bites that could crush bone and tear flesh. In contrast, smaller carnivorous dinosaurs such as Velociraptor hunted in packs, using their intelligence and coordination to take down prey much larger than themselves. These agile predators would have used their sharp claws and teeth to inflict multiple wounds, wearing down their quarry through repeated attacks. Some dinosaurs, like the long-necked Therizinosaurus, had massive claws that could have been used to defend against predators or to hook and pull down vegetation. While not primarily hunters, these omnivores could have used their formidable claws to catch small prey when the opportunity arose. Aquatic and semi-aquatic dinosaurs such as Spinosaurus likely hunted fish and other marine life, using their crocodile-like snouts and sharp teeth to snatch prey from the water. Their unique adaptations allowed them to excel in environments where other large predators could not compete, giving them access to a rich and diverse food source. Herbivorous dinosaurs developed a variety of impressive defensive strategies to protect themselves from predators. One of the most notable was the evolution of body armor. Dinosaurs like the Ankylosaurus were covered in thick, bony plates and spikes, creating a formidable living tank that even the largest carnivores would have struggled to attack. Some herbivores relied on their sheer size as a deterrent. The massive sauropods, such as Argentinosaurus, grew to such enormous proportions that most predators simply could not tackle them as adults. Their long necks also gave them an excellent vantage point to spot approaching danger. Other plant eaters developed dangerous weapons. The Stegosaurus, for instance, sported a tail lined with sharp spikes, which it could swing with tremendous force to fend off attackers. Ceratopsians like Triceratops used their horns and large frilled heads both for defense and intraspecies combat. Many herbivorous dinosaurs also adopted social behaviors as a defensive strategy. By moving in herds, they increased their chances of spotting predators and could work together to protect vulnerable members of the group. This strategy was likely employed by duck-billed dinosaurs and many other species, providing safety in numbers against the ever-present threat of carnivorous predators. Dinosaur mating rituals, while not directly observable, can be inferred from evidence in the fossil record and by studying modern animals. Many scientists believe that dinosaurs engaged in elaborate courtship displays, similar to those seen in birds and reptiles today. These displays likely involved visual signals such as colorful feathers or scales, as well as physical demonstrations of strength and fitness. For larger dinosaurs, like the long-necked sauropods, males might have engaged in neck wrestling contests to establish dominance and attract females. Theropods, including the ancestors of modern birds, probably used their forelimbs and tail feathers in intricate dances or displays. Some dinosaurs, like Protoceratops, had large frills that may have served as visual signals during courtship. Vocalizations likely played a crucial role in dinosaur mating rituals. Recent studies of dinosaur skull structures suggest that many species could produce a wide range of sounds, from low-frequency rumbles to high-pitched calls. These vocalizations could have been used to attract mates from a distance or to coordinate courtship behaviors. Scent may have also been important in dinosaur mating. Some dinosaurs had specialized glands that could have produced pheromones, chemical signals used to communicate readiness to mate. This chemical communication, combined with visual and auditory displays, would have created a complex and fascinating mating ritual for these ancient creatures. Uncovering the sleep habits of dinosaurs presents a fascinating challenge for paleontologists. While we cannot directly observe these ancient creatures in slumber, scientists have made educated inferences based on fossil evidence and comparisons with modern animals. Some dinosaurs likely exhibited sleep patterns similar to their living relatives, birds and crocodiles. Studies of dinosaur brain cases suggest that many species possessed the neurological structures necessary for sleep cycles comparable to those of contemporary animals. This indicates that dinosaurs probably experienced periods of rest and activity, much like the creatures we see today. Fossil discoveries have provided intriguing clues about dinosaur sleeping postures. Some small, bird-like dinosaurs have been found fossilized in a sleeping position, with their heads tucked under their arms, reminiscent of modern birds. This suggests that at least some dinosaur species adopted similar resting poses to conserve heat and protect vulnerable body parts. For larger dinosaurs, sleep likely posed different challenges. Some paleontologists theorize that massive sauropods, like Brachiosaurus, might have slept standing up, similar to horses or elephants. This would have allowed them to remain vigilant against predators and avoid the difficulty of rising from a prone position. However, the exact sleep patterns of these enormous creatures remain a subject of ongoing research and speculation in the scientific community. Dinosaurs possessed a range of sensory abilities that were both similar to and different from those of modern animals. Their sense of smell was highly developed, with some species like Tyrannosaurus rex having olfactory bulbs as large as those found in modern wolves. This keen sense of smell likely played a crucial role in hunting, foraging, and social interactions. Vision varied among dinosaur species. Many had eyes positioned on the sides of their heads, providing a wide field of view ideal for detecting predators. Others, particularly predatory dinosaurs, had forward-facing eyes that allowed for better depth perception, much like modern birds of prey. Some dinosaurs may have had excellent color vision, while others might have been more adept at seeing in low-light conditions. Hearing capabilities in dinosaurs were diverse. Some species, such as the duck-billed hadrosaurs, had intricate inner ear structures, suggesting they could detect a wide range of frequencies. This ability might have been used for complex vocalizations and social communication. Other dinosaurs, like the small theropods, had hearing ranges similar to those of modern birds, allowing them to perceive high-frequency sounds. Touch and balance were also important senses for dinosaurs. Many species had sensitive skin, particularly around their snouts, which they likely used to explore their environment and interact with their young. Their inner ear structures indicate that most dinosaurs had a good sense of balance, crucial for the varied lifestyles and body sizes found across different species. While not all dinosaur senses matched those of modern animals, their sensory abilities were well adapted to their specific ecological niches and survival needs. Dinosaurs thrived in a diverse array of environments across the planet during their long reign. Lush tropical forests teemed with life, providing ample vegetation for herbivorous species and hiding places for predators. These dense jungles were home to famous dinosaurs like the long-necked Brachiosaurus and the fierce Allosaurus. Vast open plains and savannas stretched across continents, supporting herds of grazing dinosaurs such as Triceratops and Stegosaurus. These grasslands also became hunting grounds for agile carnivores like Velociraptor. Coastal regions and swamplands offered unique habitats where dinosaurs like the fish-eating Spinosaurus adapted to semi-aquatic lifestyles. Arid deserts and scrublands presented challenges that some dinosaurs overcame through specialized adaptations. The hardy Protoceratops, for instance, thrived in the harsh Gobi Desert. Even polar regions hosted dinosaur life, with species like Liaelinasaura surviving in forests near the Antarctic Circle, enduring long periods of darkness each year. As the climate and geography changed over millions of years, dinosaurs continuously adapted to new environments. From scorching deserts to frigid tundras, these remarkable creatures proved their resilience and ability to inhabit nearly every terrestrial ecosystem on Earth. Dinosaur habitats underwent significant transformations throughout the Mesozoic era, reflecting the dynamic nature of Earth's changing climate and geography. During the Triassic period, the earliest dinosaurs emerged in a world dominated by a single supercontinent called Pangaea. This landmass created vast interior deserts and seasonal extremes, with dinosaurs adapting to these harsh conditions. As the Jurassic period began, Pangaea started to break apart, leading to the formation of new oceans and more diverse ecosystems. Lush forests and fern prairies spread across the land, providing ample vegetation for herbivorous dinosaurs. This period saw the rise of long-necked sauropods, which thrived in these verdant environments. The Cretaceous period brought further changes, with the continents continuing to drift apart. Flowering plants evolved and spread rapidly, altering the plant communities that dinosaurs depended on. Coastal areas and inland seas became more prevalent, creating new habitats for marine reptiles and shore-dwelling dinosaurs. The climate generally became warmer and more humid, supporting diverse ecosystems from tropical jungles to temperate forests. These habitat changes drove the evolution and diversification of dinosaurs throughout the Mesozoic. As environments shifted, dinosaurs adapted to new food sources, developed different locomotion styles, and evolved various defense mechanisms. The end of the Cretaceous saw a cooling trend and sea level changes, setting the stage for the dramatic extinction event that would mark the end of the dinosaurs' reign. Dinosaurs were dominant land animals for over 160 million years, shaping and influencing the ecosystems they inhabited in profound ways. As diverse creatures, they occupied various ecological niches, from towering herbivores to swift carnivores, each playing a crucial role in maintaining the balance of their environments. Large herbivorous dinosaurs, such as the long-necked sauropods, acted as primary consumers, feeding on vast quantities of vegetation. Their feeding habits helped shape the landscape, influencing plant evolution and distribution. These massive creatures also served as mobile ecosystems themselves, hosting numerous smaller organisms and parasites. Carnivorous dinosaurs, ranging from the small and agile to the enormous apex predators like Tyrannosaurus rex, were key in controlling herbivore populations. This predator-prey relationship drove evolutionary adaptations in both groups, leading to the development of various defensive and offensive features we observe in fossil records. The activities of dinosaurs also contributed to nutrient cycling within their ecosystems. Their movement, feeding, and waste production helped distribute nutrients across landscapes, supporting plant growth and smaller organisms. Even in death, dinosaur remains provided vital resources for scavengers and decomposers, further contributing to the complex web of life in prehistoric ecosystems. Plant life underwent significant changes during the age of dinosaurs, evolving alongside these magnificent creatures for over 160 million years. As dinosaurs roamed the earth, plants adapted and diversified, creating lush landscapes that served as both food sources and habitats for these prehistoric animals. The Triassic period marked the beginning of dinosaur dominance, and during this time, the plant world was primarily composed of ferns, cycads, and conifers. These hardy plants thrived in the warm, dry climate of the era. As dinosaurs evolved and grew larger, plants developed new strategies to survive, including tougher leaves and protective structures to deter herbivorous dinosaurs from overgrazing. The Jurassic period saw the emergence of more diverse plant life, including the first flowering plants, or angiosperms. This development revolutionized the plant world and had a profound impact on dinosaur evolution. Flowering plants provided new food sources and habitats, leading to the diversification of herbivorous dinosaurs and the animals that preyed upon them. By the Cretaceous period, flowering plants had become dominant, transforming the landscape into something more recognizable to modern eyes. This shift in plant life coincided with the evolution of some of the most iconic dinosaur species, such as Tyrannosaurus rex and Triceratops. The complex relationships between plants and dinosaurs shaped both groups, driving the evolution of new species and ecological niches until the mass extinction event that marked the end of the dinosaur era. During the age of dinosaurs, a diverse array of animals shared the Earth alongside these iconic reptiles. Mammals, though small and relatively unassuming at the time, were present throughout the dinosaur era. These early mammals were mostly nocturnal creatures, resembling modern-day shrews or rodents. The skies were home to flying reptiles called pterosaurs, ranging from small gliders to massive creatures with wingspans as wide as a small airplane. In the oceans, large marine reptiles like plesiosaurs, ichthyosaurs, and mosasaurs dominated the waters, coexisting with ancient sharks and ray-finned fishes. Crocodiles and their relatives were also contemporaries of dinosaurs, along with turtles and lizards. Amphibians, including early frogs and salamanders, inhabited freshwater environments. Insects, including ancient relatives of modern beetles, flies, and dragonflies, were abundant and diverse. As the dinosaur era progressed, birds evolved from a group of small, feathered dinosaurs, becoming increasingly diverse and widespread. This rich tapestry of life forms created complex ecosystems that thrived alongside the dinosaurs for millions of years, each playing a crucial role in the ancient world. Dinosaurs were dominant land animals for over 160 million years, shaping and influencing their environments in profound ways. As large herbivores, many dinosaur species significantly impacted plant life. Sauropods, the long-necked giants, consumed vast amounts of vegetation, altering forest structures and plant distributions. Their feeding habits likely promoted the growth of certain plant species while limiting others, much like modern elephants do in African savannas. Carnivorous dinosaurs played crucial roles in maintaining ecosystem balance. By preying on herbivores, they controlled population sizes and influenced the behavior of their prey. This predator-prey dynamic led to evolutionary adaptations in both groups, such as increased speed, defensive structures, and enhanced sensory capabilities. Dinosaurs also affected their environments through their physical presence. Large species created pathways through forests, trampled vegetation, and compacted soil. Their droppings fertilized the ground, dispersed seeds, and supported diverse communities of insects and microorganisms. Even in death, dinosaur carcasses provided nutrients to scavengers and decomposers, enriching the soil. The impact of dinosaurs extended to early mammals, which evolved alongside them. Many early mammals were small and nocturnal, likely adapting to avoid competition and predation from dinosaurs. This set the stage for mammalian diversification after the dinosaurs' extinction, ultimately leading to the rise of modern mammals, including humans. Dinosaurs roamed the Earth for over 160 million years, inhabiting a wide variety of landscapes that were quite different from what we see today. During the Mesozoic era, the continents were arranged differently, creating unique environments and ecosystems. One striking landscape was the vast desert that covered much of the supercontinent Pangaea. This arid expanse was home to hardy dinosaurs like the Chelophysis, which thrived in the harsh conditions. As Pangaea began to break apart, lush coastal regions emerged, supporting a diverse array of plant-eating dinosaurs and their predators. In the Jurassic period, dense conifer forests covered much of the land, providing habitat for massive sauropods like Brachiosaurus. These towering trees were interspersed with primitive flowering plants, creating a green world unlike any forest we know today. Alongside these forests, expansive fern prairies stretched as far as the eye could see, offering grazing grounds for herds of herbivorous dinosaurs. The Cretaceous period saw the rise of flowering plants, transforming the landscape into something more familiar to modern eyes. However, the climate was much warmer, and polar regions were free of ice. Dinosaurs like Dinosaur inhabited temperate forests near the South Pole, enduring months of winter darkness. These unique prehistoric landscapes shaped the evolution of dinosaurs, allowing them to diversify and dominate the Earth for millions of years. Sea level changes during the age of dinosaurs played a crucial role in shaping their habitats and influencing their evolution. Throughout the Mesozoic era, which lasted from about 252 million years ago to 66 million years ago, Earth experienced significant fluctuations in sea levels. These changes were primarily driven by variations in global climate and tectonic activity. During periods of higher sea levels, vast areas of land were submerged, creating extensive shallow seas and coastal environments. This led to the formation of new habitats such as estuaries, lagoons, and coral reefs, which provided diverse ecosystems for marine reptiles and fish. On land, the rising waters fragmented once continuous landmasses, isolating populations of dinosaurs and spurring the evolution of new species adapted to island living. Conversely, when sea levels dropped, new land bridges emerged, connecting previously isolated areas. This allowed dinosaurs to migrate and colonize new territories, leading to increased competition and further evolutionary adaptations. The exposed seafloor also created vast coastal plains, providing expansive grazing grounds for herbivorous dinosaurs and hunting territories for carnivores. These sea level fluctuations had far-reaching effects on global climate patterns, altering temperatures, rainfall, and vegetation distribution. As a result, dinosaurs had to continually adapt to changing environmental conditions, driving the remarkable diversity of species we observe in the fossil record. The interplay between sea levels and dinosaur habitats highlights the dynamic nature of Earth's ecosystems and the profound impact of geological processes on the evolution of life. Fossil discoveries in polar regions have provided compelling evidence that dinosaurs once thrived in these extreme environments. In the Arctic Circle, paleontologists have unearthed numerous dinosaur fossils, including those of hadrosaurs, theropods, and ceratopsians. These findings suggest that diverse dinosaur communities existed in what are now the northernmost parts of North America and Eurasia. Similarly, in Antarctica, scientists have found fossils of several dinosaur species, challenging our previous understanding of dinosaur habitats. Notably, the discovery of a 190-million-year-old sauropodomorph fossil on the Antarctic Peninsula indicates that these long-necked herbivores lived on the continent long before it drifted to its current position at the South Pole. These polar dinosaurs likely adapted to their environments in fascinating ways. Some species may have developed enhanced night vision to cope with months of winter darkness, while others might have had higher metabolic rates to withstand colder temperatures. Certain fossils even suggest that some polar dinosaurs may have been warm-blooded, allowing them to remain active during colder months. The presence of dinosaur fossils in these regions also provides valuable information about past climates. During the Mesozoic era, polar regions were warmer than they are today, supporting lush forests and diverse ecosystems. This evidence of polar dinosaurs not only expands our understanding of these ancient creatures, but also offers insights into Earth's climate history and the adaptability of life in extreme conditions. Changing climates played a crucial role in shaping dinosaur distribution across the planet. As temperatures fluctuated over millions of years, dinosaurs adapted and migrated to survive in new environments. During warmer periods, many species thrived and expanded their ranges, while cooler times forced them to retreat to more hospitable regions. The Cretaceous period, which lasted from about 145 million to 66 million years ago, saw significant climate shifts that impacted dinosaur populations. As the world became warmer and wetter, lush forests and diverse ecosystems spread across the continents. This allowed plant-eating dinosaurs to flourish and diversify, which in turn supported a greater variety of carnivorous species. However, not all climate changes were beneficial. Cooling trends could lead to the contraction of tropical and subtropical zones, reducing suitable habitats for many dinosaur species. This forced them to adapt to new food sources or move to areas with more favorable conditions. Some dinosaurs developed specialized features to cope with changing environments, such as the hadrosaurs evolving complex tooth batteries to process tougher plant material in drier climates. The ultimate climate change event, triggered by the asteroid impact at the end of the Cretaceous, led to the extinction of non-avian dinosaurs. This catastrophic shift in global climate demonstrates the profound impact that environmental changes can have on species distribution and survival. Tyrannosaurus rex was one of the most fearsome predators to ever walk the Earth. This massive theropod dinosaur, which lived during the late Cretaceous period about 68 to 66 million years ago, possessed a unique combination of physical attributes that made it an apex predator. The most striking feature of Tyrannosaurus rex was its enormous skull, measuring up to 5 feet in length. This skull housed a set of powerful jaws lined with serrated teeth, each as long as a human hand. These teeth were not just sharp, they were robust and could crush bone, allowing Tyrannosaurus to make full use of its prey. The bite force of Tyrannosaurus rex was estimated to be among the strongest of any terrestrial animal, capable of exerting a force of several thousand kilograms. Despite its massive size, with adults reaching lengths of 40 feet and weighing up to 7 tons, Tyrannosaurus rex was surprisingly agile. Its strong legs allowed it to reach speeds of up to 25 miles per hour in short bursts. This combination of speed and power made it a formidable hunter, capable of chasing down prey or ambushing them from hiding spots. Tyrannosaurus rex also possessed keen senses, particularly its vision and sense of smell. Its eyes were positioned for binocular vision, giving it excellent depth perception, crucial for judging distances when hunting. Its olfactory bulbs were also highly developed, suggesting a powerful sense of smell that could have been used to detect prey from great distances. These sensory adaptations, combined with its physical prowess, made Tyrannosaurus rex a supreme predator of its time. Brachiosaurus was one of the largest dinosaurs to ever walk the Earth. This colossal sauropod, which lived during the late Jurassic period approximately 150 million years ago, could reach staggering proportions. Based on fossil evidence, scientists estimate that Brachiosaurus could grow up to 85 feet in length from head to tail. To put this into perspective, that is about the length of 2.5 school buses placed end to end. The height of Brachiosaurus was equally impressive. At its tallest point, which was the top of its head, this gentle giant could reach up to 50 feet high. This means it could easily peer into a 5th-story window of a modern building. The immense size of Brachiosaurus was not just for show, it allowed the dinosaur to reach high into the treetops to feed on vegetation that other herbivores could not access. Despite its enormous size, Brachiosaurus was not the heaviest dinosaur. Its weight is estimated to have been between 30 and 50 tons. While this may seem incredibly heavy, some other sauropods, like Argentinosaurus, may have weighed even more. The relatively lighter weight of Brachiosaurus, compared to its size, was due to its unique body structure and the presence of air sacs in its bones, a feature shared with modern birds. Stegosaurus, a dinosaur that lived during the late Jurassic period, had a truly remarkable set of plates and spikes that set it apart from other prehistoric creatures. Along its back, Stegosaurus sported a double row of large, upright, bony plates. These plates were not solid bone, but rather consisted of a rigid outer layer filled with blood vessels. Scientists believe these plates might have served multiple purposes, including regulating body temperature and visual display. The arrangement of these plates was distinctive, alternating rather than forming matching pairs on either side of the spine. This asymmetrical layout created a more effective surface area for heat absorption and dissipation. At the end of its tail, Stegosaurus wielded a formidable defense mechanism, a cluster of 4 long, sharp spikes known as the thagomizer. These spikes, which could reach up to 3 feet in length, were likely used for protection against predators. The combination of plates and spikes made Stegosaurus a well-defended herbivore. Its plates could have acted as a deterrent to predators, making the dinosaur appear larger and more intimidating. Meanwhile, the tail spikes provided an active defense, capable of inflicting serious damage to any attacker. Fossil evidence has even revealed puncture wounds in predator bones that match the shape and size of Stegosaurus spikes. Interestingly, the plates and spikes of Stegosaurus varied in size and shape between different species and possibly between males and females. This variation suggests that these features might have also played a role in species recognition and possibly even courtship displays, adding another layer of complexity to their function beyond defense and thermoregulation. Velociraptor, contrary to its portrayal in popular culture, was much smaller than commonly depicted. In reality, this dinosaur was about the size of a turkey, standing around 1/2 meter tall and measuring about 2 meters long from snout to tail. Its weight was comparable to that of a medium-sized dog, roughly 15 to 20 kilograms. The misconception about Velociraptor's size stems largely from the movie Jurassic Park, which featured much larger dromaeosaurids more closely resembling Deinonychus or Utahraptor. These larger relatives of Velociraptor were used as inspiration for the film's creatures, but were still called velociraptors for dramatic effect. Paleontological evidence, including numerous fossil specimens, clearly shows that Velociraptor was a small, agile predator. It had a long, low skull, a sickle-shaped killing claw on each foot, and was likely covered in feathers. Despite its diminutive size, Velociraptor was a formidable hunter, probably preying on small to medium-sized animals. This discrepancy between scientific reality and popular depiction highlights the importance of accurate scientific communication. While artistic license can create compelling narratives, it is crucial to distinguish between fact and fiction, especially when it comes to our understanding of prehistoric life. Triceratops, one of the most recognizable dinosaurs, had a truly remarkable head that set it apart from other prehistoric creatures. The most striking feature was its large, bony frill, which extended from the back of the skull, creating a shield-like structure. This frill could reach up to 6 feet across in the largest specimens, giving Triceratops an imposing profile. Above its beaked mouth, Triceratops sported 3 horns, which gave the dinosaur its name, meaning three-horned face in Greek. Two large horns protruded from above its eyes, while a smaller horn sat on its snout. These horns varied in size and shape among different species of Triceratops, but they were always a defining characteristic. The Triceratops' skull was massive, sometimes making up nearly 1/3 of the animal's entire body length. This disproportionately large head housed powerful jaw muscles, allowing Triceratops to efficiently process the tough plant material that made up its diet. The beak-like structure at the front of its mouth was ideal for snipping off vegetation. Scientists believe the frill and horns served multiple purposes. They likely played a role in species recognition and may have been used in mating displays. Additionally, these features probably provided defense against predators like Tyrannosaurus rex, making Triceratops a formidable opponent despite being an herbivore. Ankylosaurus, a formidable armored dinosaur from the late Cretaceous period, wielded its distinctive club-like tail as a powerful defensive weapon. This hefty appendage, composed of fused vertebrae and large bony knobs, served as a formidable deterrent against predators. When threatened, Ankylosaurus could swing its tail with considerable force, potentially delivering bone-crushing blows to attackers. This natural club was particularly effective against large carnivorous dinosaurs that might have targeted Ankylosaurus. The tail's design allowed for quick, powerful strikes, making it an efficient tool for self-defense. Recent studies suggest that the tail club might have also played a role in intra-species competition. Male Ankylosaurus may have used their tails in contests for territory or mates, similar to how some modern animals use horns or antlers. This dual-purpose weapon highlights the evolutionary adaptations that helped Ankylosaurus survive in a world filled with fearsome predators. The effectiveness of the tail club, combined with Ankylosaurus's heavily armored body, made it one of the best-defended herbivores of its time. This unique adaptation contributed to the success of Ankylosaurus, allowing it to thrive until the end of the dinosaur era. Spinosaurus, one of the largest known carnivorous dinosaurs, possessed a truly remarkable feature: an enormous sail-like structure on its back. This sail, composed of elongated neural spines covered in skin, stretched from the dinosaur's neck to its tail, creating a striking profile unlike any other known prehistoric creature. The sail of Spinosaurus was not just for show. Scientists believe it served multiple purposes, making it a crucial adaptation for this ancient predator. One primary function was likely thermoregulation. The large surface area of the sail could have helped Spinosaurus control its body temperature by absorbing heat when basking in the sun or dissipating excess heat in cooler environments. Additionally, the sail might have played a role in mate selection and species recognition. Its size and shape could have been a visual signal to potential mates or rivals, much like the elaborate displays seen in modern animals. Some researchers have also suggested that the sail might have been brightly colored or patterned, further enhancing its visual impact. Interestingly, the sail's structure also provides clues about Spinosaurus's lifestyle. The dense blood vessel network within the neural spines suggests that the sail was highly vascularized, supporting the theory of its use in thermoregulation. This adaptation, combined with other unique features like its elongated snout and dense bones, points to Spinosaurus being a semi-aquatic predator, well suited for hunting in and around water environments of the Cretaceous period. Parasaurolophus, the remarkable duck-billed dinosaur, sported an impressive hollow crest that extended from the back of its skull. This distinctive feature has long fascinated paleontologists and dinosaur enthusiasts alike. Scientists believe the crest served multiple purposes, each contributing to the dinosaur's survival and social interactions. One primary function of the Parasaurolophus crest was likely communication. The hollow structure acted as a natural resonating chamber, allowing the dinosaur to produce loud, low-frequency sounds. These vocalizations could have been used to signal danger, attract mates, or maintain contact with other members of the herd across vast distances. The crest might have also played a role in visual displays. Its size and shape could have varied between individuals, potentially indicating age, sex, or social status within the herd. This visual differentiation might have been crucial for mate selection and establishing dominance hierarchies among Parasaurolophus groups. Some researchers have suggested that the crest might have helped regulate the dinosaur's body temperature. The large surface area could have facilitated heat exchange with the environment, allowing Parasaurolophus to cool down more efficiently in hot climates or warm up in cooler conditions. However, this theory remains a subject of debate among paleontologists, with ongoing research continually shedding new light on the fascinating world of these ancient creatures. Therizinosaurus, a fascinating dinosaur from the late Cretaceous period, possessed some of the largest claws ever seen in the animal kingdom. These massive claws, which could grow up to 1 meter in length, were not primarily used for hunting or defense, as one might expect. Instead, they served a variety of unique purposes that suited the lifestyle of this unusual theropod. The enormous claws of Therizinosaurus evolved as adaptations to its herbivorous diet. Unlike many of its carnivorous theropod relatives, Therizinosaurus was a plant eater. Its long claws were excellent tools for reaching and grasping vegetation, allowing it to pull down branches from tall trees and strip them of leaves. This adaptation enabled Therizinosaurus to access food sources that might have been out of reach for other herbivorous dinosaurs. Additionally, these impressive claws likely played a role in self-defense. While not primarily used as weapons, their sheer size and intimidating appearance would have been a strong deterrent to potential predators. The claws may have also been useful for digging, perhaps to uncover roots or tubers, or to create nests for laying eggs. The evolution of such extreme features in Therizinosaurus highlights the diverse and sometimes unexpected paths that natural selection can take. These enormous claws represent a remarkable example of how body parts can be repurposed and adapted to suit new ecological niches, demonstrating the incredible diversity and adaptability of dinosaur species throughout their long reign on Earth. Archaeopteryx played a pivotal role in our understanding of dinosaur evolution, serving as a critical link between dinosaurs and birds. Discovered in the late 19th century in Germany, this remarkable fossil exhibited features of both dinosaurs and modern birds, effectively bridging the evolutionary gap between these two groups. The significance of Archaeopteryx lies in its unique combination of characteristics. It possessed dinosaur-like features such as a long bony tail, clawed fingers, and teeth, while also displaying distinctly avian traits like feathers and a wishbone. This mosaic of features provided compelling evidence for the theory that birds evolved from theropod dinosaurs, a group that includes well-known species like Velociraptor and Tyrannosaurus rex. The presence of well-preserved feathers in Archaeopteryx fossils was particularly groundbreaking. It demonstrated that feathers evolved in dinosaurs long before the emergence of powered flight, suggesting that they may have initially served other purposes, such as insulation or display. This discovery prompted scientists to re-evaluate their understanding of feather evolution and the diversity of feathered dinosaurs. Furthermore, Archaeopteryx helped reshape our perception of dinosaur biology and behavior. Its discovery challenged the notion that dinosaurs were purely cold-blooded reptiles, instead suggesting that some dinosaurs may have been warm-blooded and highly active, much like modern birds. This shift in perspective has had far-reaching implications for how we interpret dinosaur fossils and reconstruct prehistoric ecosystems. Dinosaurs exhibited a diverse range of dietary habits, adapting to various ecological niches over their long reign on Earth. The two primary categories of dinosaur diets were herbivory and carnivory, with some species developing more specialized feeding strategies within these broad groups. Herbivorous dinosaurs, which fed exclusively on plants, were the most common type. These plant eaters evolved a variety of methods to process tough vegetation. Some, like the long-necked sauropods, were generalist browsers, consuming a wide range of plant materials from trees and shrubs. Others, such as the horned ceratopsians and duck-billed hadrosaurs, developed specialized beaks and teeth for cropping and grinding tougher plants closer to the ground. Carnivorous dinosaurs, on the other hand, preyed on other animals. The most famous of these were the theropods, including the formidable Tyrannosaurus rex. These predators had sharp, serrated teeth, ideal for tearing flesh. Some carnivores were generalists, eating whatever prey they could catch, while others may have specialized in hunting specific types of animals or scavenging. Interestingly, some dinosaurs developed omnivorous diets, combining both plant matter and meat in their food intake. This dietary flexibility likely gave them an advantage in changing environments. As we continue to study fossilized remains and trace evidence, our understanding of dinosaur diets continues to evolve, revealing the complex and fascinating ecological relationships of these ancient creatures. Herbivorous dinosaurs developed remarkable adaptations to process the tough plant material that formed their diet. These ancient creatures possess specialized digestive systems and teeth that allowed them to break down fibrous vegetation efficiently. Many herbivorous dinosaurs had batteries of teeth designed for grinding plant matter. Species like Triceratops had rows of teeth that worked like scissors, shearing through leaves and stems. As these teeth wore down, they were continuously replaced, ensuring the dinosaur always had sharp cutting edges. Some dinosaurs, such as hadrosaurs, had thousands of teeth arranged in complex dental batteries that acted like built-in food processors. To aid digestion, many herbivorous dinosaurs swallowed stones called gastroliths. These stones accumulated in their stomachs and helped grind down plant material, much like the gizzards in modern birds. This mechanical breakdown of food increased the surface area for digestive enzymes to act upon, maximizing nutrient extraction. Some scientists believe that certain herbivorous dinosaurs might have had gut bacteria similar to those found in modern ruminants like cows. These microorganisms would have helped break down cellulose, the tough structural component of plants, allowing the dinosaurs to extract more nutrients from their plant-based diet. This combination of physical and biological adaptations enabled herbivorous dinosaurs to thrive on the vegetation of their time, fueling their often massive bodies. Carnivorous dinosaurs evolved a range of impressive adaptations that made them formidable predators. Their most notable feature was their array of sharp, serrated teeth, perfect for slicing through flesh and crunching bones. These teeth were continually replaced throughout their lives, ensuring they always had a set of razor-sharp tools at their disposal. Many carnivorous dinosaurs also developed powerful legs and clawed feet, allowing them to chase down prey at high speeds. Some, like the famous Tyrannosaurus rex, had relatively short but muscular arms with sharp claws, useful for grasping struggling prey. Others, such as the Deinonychus, sported a large, sickle-shaped claw on each foot, which they likely used to deliver devastating slashing attacks. Enhanced senses played a crucial role in their hunting success. Many carnivorous dinosaurs had large eyes, providing excellent vision for spotting prey from a distance. Some species also developed highly sensitive olfactory systems, enabling them to track prey by scent. Additionally, certain carnivores, like the velociraptor, are believed to have had keen hearing, helping them locate potential meals in dense forests or during nighttime hunts. Intelligence was another key adaptation. Fossil evidence suggests that some carnivorous dinosaurs, particularly the smaller, agile species, had relatively large brains for their body size. This increased cognitive capacity likely allowed for more complex hunting strategies, including potential pack hunting behaviors in some species. These combined adaptations made carnivorous dinosaurs incredibly successful predators, dominating terrestrial ecosystems for millions of years. Sauropods, the largest land animals to ever roam the Earth, faced a monumental challenge in consuming enough food to fuel their enormous bodies. These long-necked, plant-eating giants employed several strategies to meet their immense dietary needs. One key adaptation was their highly efficient digestive system. Sauropods had large, barrel-shaped bodies that housed complex digestive tracts. These specialized gut systems allowed them to extract maximum nutrients from the plant matter they consumed, making the most of every bite. Their digestive process likely involved fermentation, similar to modern-day cows, which helped break down tough plant fibers. Another crucial factor was their feeding technique. Sauropods used their long necks to reach high into trees, accessing food sources that other herbivores couldn't. This allowed them to consume vast quantities of vegetation without expending much energy moving around. Their teeth were adapted for stripping leaves from branches rather than chewing, enabling them to swallow food quickly and continue eating. Sauropods also benefited from the lush, warm environments of the Mesozoic era. The abundance of plant life during this time provided a constant supply of food. These dinosaurs likely spent most of their waking hours eating, continuously processing food to meet their energy requirements. Their massive size, while demanding in terms of food intake, also allowed them to survive on lower-quality plant matter that smaller herbivores couldn't subsist on, giving them a competitive edge in their prehistoric ecosystems. Paleontologists have uncovered fascinating evidence of dinosaur feeding behaviors through various fossil discoveries and scientific analysis. One compelling source of information comes from fossilized stomach contents, which provide direct insight into what dinosaurs ate. These rare finds have revealed plant material in herbivorous dinosaurs and bones of prey animals in carnivorous species. Tooth marks on fossilized bones offer another valuable clue. Scientists can determine the size and shape of the teeth that made these marks, helping to identify which dinosaur species were responsible for specific predation or scavenging events. Additionally, coprolites, or fossilized feces, have been analyzed to reveal undigested plant matter, bone fragments, and other dietary components. The structure of dinosaur teeth and jaws also provides important evidence of their feeding habits. Sharp, serrated teeth in carnivorous dinosaurs indicate a diet of meat, while flat, grinding teeth in herbivores suggest a plant-based diet. Some dinosaurs, like Tyrannosaurus rex, had incredibly powerful jaws capable of crushing bone, implying they could consume entire prey animals. Trace fossils, such as footprints and feeding traces on plants, offer further insights. Paleobotanists have identified specific damage patterns on fossilized leaves that match the dental anatomy of certain herbivorous dinosaurs. This evidence allows scientists to reconstruct not only what dinosaurs ate, but also how they fed, providing a more complete picture of their ecological roles and behaviors in prehistoric ecosystems. Dinosaur teeth evolved in remarkable ways to suit a wide variety of diets. Carnivorous dinosaurs like Tyrannosaurus rex developed large, serrated teeth perfect for tearing flesh and crushing bone. These fearsome teeth could grow up to 12 inches long and were constantly replaced throughout the dinosaur's life. Herbivorous dinosaurs, on the other hand, had teeth adapted for their plant-based diets. Some, like the duck-billed hadrosaurs, possess thousands of small, tightly packed teeth that formed a grinding surface ideal for breaking down tough vegetation. These dinosaurs could have up to 800 teeth in their mouths at once, with new teeth constantly growing to replace worn ones. Other plant eaters, such as the long-necked sauropods, had peg-like teeth suited for stripping leaves from branches. These teeth were replaced rapidly, sometimes as often as once a month, to keep up with the wear from their abrasive diet. Interestingly, some dinosaurs like Triceratops had beaks made of keratin in addition to teeth. This combination allowed them to both crop plants and process tougher materials efficiently, showcasing the diverse adaptations that evolved to exploit different food sources in the Mesozoic era. Dinosaurs evolved a wide array of fascinating feeding strategies over their long reign on Earth. One of the most unusual was employed by the therizinosaurs, bizarre dinosaurs with enormous claws on their hands. Rather than using these claws as weapons, they likely used them to pull down branches, allowing them to browse on vegetation high in the trees. This adaptation let them access food sources other herbivores couldn't reach. Another peculiar feeding method was seen in the duck-billed hadrosaurs. These dinosaurs had hundreds of teeth arranged in complex dental batteries, allowing them to efficiently grind tough plant material. As their teeth wore down, new ones would continuously replace them, creating a self-sharpening system that kept their mouths ready for constant foraging. The long-necked sauropods developed a different approach to feeding. Some species, like Nigersaurus, had wide, square jaws filled with hundreds of small teeth. This allowed them to efficiently crop vegetation close to the ground, much like a prehistoric lawnmower. Their unique jaw structure and tooth arrangement made them highly specialized feeders, adapted to specific plant types in their environment. Lastly, some carnivorous dinosaurs developed unexpected feeding strategies. Spinosaurus, with its crocodile-like snout and conical teeth, is now believed to have been at least partially aquatic, hunting fish in rivers and swamps. This semi-aquatic lifestyle was a major departure from the land-based hunting of most other large carnivorous dinosaurs, showcasing the diverse ways these ancient reptiles adapted to fill different ecological niches. Dinosaur diets underwent significant transformations as these prehistoric creatures matured from juveniles to adults. This dietary shift was crucial for their survival and played a key role in shaping their ecosystems. Many young dinosaurs started life as opportunistic omnivores, consuming a variety of small prey and plants. This diverse diet provided the necessary nutrients for rapid growth. As they increased in size, their dietary needs and capabilities evolved. Some species that were primarily herbivorous as adults, such as the long-necked sauropods, began life eating a mix of plants and small animals before transitioning to a fully plant-based diet. Carnivorous dinosaurs like Tyrannosaurus rex experienced perhaps the most dramatic dietary changes. Juvenile tyrannosaurs had slender, blade-like teeth suited for slicing flesh from smaller prey. As they grew, their teeth became larger and more robust, capable of crushing bone. This transformation allowed adult tyrannosaurs to tackle much larger prey and exploit different food sources than their younger counterparts. The changing diets of growing dinosaurs had far-reaching effects on their ecosystems. It meant that different age groups within the same species often occupied distinct ecological niches, reducing competition for resources. This dietary flexibility likely contributed to the success and longevity of dinosaurs as a group, allowing them to dominate terrestrial ecosystems for over 160 million years. Gastroliths were an essential part of the digestive system for many plant-eating dinosaurs. These smooth, rounded stones, also known as stomach stones, were swallowed by dinosaurs and stored in their gizzards. The primary function of gastroliths was to help grind down tough plant material that the dinosaurs consumed. Unlike mammals, dinosaurs lacked teeth suitable for thoroughly chewing their food. Instead, they relied on gastroliths to mechanically break down plant matter in their digestive tract. As the muscular walls of the gizzard contracted, the gastroliths would grind against each other and the plant material, effectively pulverizing it into smaller, more digestible pieces. This process was particularly important for herbivorous dinosaurs that fed on fibrous vegetation. Species such as sauropods, which included some of the largest land animals ever to exist, are believed to have used gastroliths extensively. The stones allowed these massive creatures to extract maximum nutrition from their plant-based diets, supporting their enormous body sizes. Paleontologists have found evidence of gastroliths in fossil remains, sometimes preserved within the body cavity of dinosaur specimens. These discoveries have provided valuable insights into dinosaur diets and digestive processes, helping scientists better understand the ecological roles these ancient creatures played in their prehistoric environments. Herbivorous dinosaurs developed a variety of strategies to partition food resources, allowing multiple species to coexist in the same ecosystems. These adaptations were crucial for reducing competition and ensuring each group could access the nutrients they needed to thrive. One key factor in resource partitioning was the height at which different dinosaurs fed. Long-necked sauropods, such as Brachiosaurus and Diplodocus, could reach the tallest trees, browsing on leaves and branches that were inaccessible to other herbivores. In contrast, smaller plant eaters like Stegosaurus and Iguanodon focused on low-growing vegetation, including ferns, cycads, and shrubs. Differences in tooth structure and jaw mechanics also played a significant role. Some dinosaurs, like the duck-billed hadrosaurs, had complex dental batteries with hundreds of teeth, allowing them to efficiently process tough, fibrous plants. Others, such as the horned ceratopsians, had sharp beaks and shearing teeth that were better suited for slicing through tougher vegetation. Additionally, some herbivorous dinosaurs developed specialized digestive systems to extract nutrients from different types of plant matter. This allowed them to occupy distinct dietary niches even when feeding on similar plants. By evolving these varied adaptations, herbivorous dinosaurs were able to coexist and thrive in diverse ecosystems throughout the Mesozoic era. Dinosaurs laid their eggs in a manner similar to modern birds and reptiles. Female dinosaurs would deposit their eggs in carefully chosen nesting sites, often in groups called clutches. These nests varied in structure depending on the species, with some creating simple depressions in the ground, while others constructed more elaborate nests using vegetation. The process of egg-laying itself was likely similar to what we observe in modern reptiles. The female dinosaur would position herself over the nesting area and release the eggs one by one. Dinosaur eggs came in various shapes and sizes, from the small, round eggs of some theropods to the larger, elongated eggs of sauropods. Many dinosaur species exhibited parental care, with some guarding their nests and others possibly incubating the eggs by sitting on them or covering them with organic material. This behavior helped protect the eggs from predators and maintain the optimal temperature for embryo development. Fossil evidence has revealed fascinating details about dinosaur reproduction. Some specimens show dinosaurs fossilized while sitting on their nests, providing direct evidence of brooding behavior. Other fossils have preserved entire clutches of eggs, giving scientists valuable insights into dinosaur reproductive strategies and the diversity of their egg-laying habits. Dinosaur nesting behaviors have been revealed through remarkable fossil discoveries and careful scientific analysis. Paleontologists have uncovered numerous dinosaur nesting sites, providing valuable insights into how these ancient creatures cared for their young. Many dinosaur species, particularly among the theropods and ornithischians, built nests for their eggs. These nests varied in structure and size, from simple scrapes in the ground to more elaborate constructions of mud and vegetation. Some dinosaurs, like the duck-billed hadrosaurs, created large nesting colonies, suggesting a degree of social behavior during breeding seasons. Fossil evidence indicates that some dinosaur parents, especially among the theropods, exhibited brooding behavior similar to modern birds. They would sit on their nests to incubate the eggs and protect them from predators. This behavior is particularly evident in small, feathered dinosaurs like Oviraptor, which was once mistakenly thought to be an egg thief but was later recognized as a devoted parent. Perhaps most intriguingly, some dinosaur species arrange their eggs in specific patterns within the nest. Sauropods, for example, often laid their eggs in neat, circular arrangements. This careful placement might have helped regulate egg temperature or protect them from damage. These nesting behaviors provide a fascinating glimpse into the parental care and reproductive strategies of creatures that lived millions of years ago, bridging the gap between ancient dinosaurs and their modern bird descendants. The time it took for dinosaur species to reach maturity varied widely, reflecting the incredible diversity of these ancient creatures. Smaller dinosaurs, like the chicken-sized Compsognathus, likely reached adulthood in just a few years. These swift predators needed to grow quickly to survive in their challenging environments. In contrast, the massive sauropods, such as Brachiosaurus and Diplodocus, took much longer to reach full size. These gentle giants required up to 3 decades to attain their impressive adult proportions. Their slow growth rate allowed them to reach enormous sizes without overtaxing their bodies during development. Tyrannosaurus rex, one of the most famous predatory dinosaurs, fell somewhere in between. Studies of fossilized bones suggest that T. rex reached sexual maturity around 15 to 20 years of age. However, it continued to grow for several more years, reaching its full size in its late 20s or early 30s. Interestingly, some dinosaurs, like the horned Triceratops, showed rapid growth in their early years, but slowed down as they approached adulthood. This growth pattern, similar to that of modern-day mammals, allowed them to quickly reach a size where they could better defend themselves against predators. Fossil evidence has provided fascinating insights into dinosaur parental behavior, revealing that many species were attentive caregivers. One of the most compelling examples comes from nesting sites discovered in Montana, where adult Maiasaura, or good mother lizard, fossils were found alongside their young. These nests contained eggs, hatchlings, and juveniles at various stages of development, suggesting that parents tended to their offspring for extended periods. Further evidence of parental care has been uncovered in the form of adult dinosaurs fossilized while brooding their nests. The oviraptor, once mistakenly thought to be an egg thief, was later found to be protecting its own eggs. Fossils show these dinosaurs in a brooding position, with their limbs arranged around a clutch of eggs, much like modern birds. Trackways have also provided valuable clues about dinosaur family life. Footprint fossils of sauropods, the long-necked giants of the dinosaur world, show adults walking alongside smaller tracks, indicating that parents traveled with their young. This behavior suggests a level of protection and guidance for juvenile dinosaurs as they navigated their environment. Perhaps most intriguingly, some dinosaur species may have even fed their young after hatching. Fossilized remains of young Allosaurus with teeth marks matching adult Allosaurus jaws hint at the possibility of parents regurgitating food for their offspring, a behavior seen in many modern birds. These diverse lines of evidence paint a picture of dinosaurs as complex, nurturing creatures, challenging earlier notions of them as simply cold-blooded, instinct-driven animals. Dinosaur growth rates were remarkably different from those of modern reptiles and more similar to birds, their living descendants. Unlike the slow, steady growth of today's reptiles, many dinosaurs experienced rapid growth spurts during their early years, allowing them to reach massive sizes relatively quickly. Evidence from fossilized bone structures reveals that some dinosaurs could grow as much as 2,000 pounds per year during their peak growth periods. This is vastly faster than modern reptiles like crocodiles or lizards, which might only gain a few pounds annually. The rapid growth of dinosaurs is more akin to that of modern birds, particularly large, flightless birds like ostriches. Interestingly, not all dinosaurs grew at the same rate. Some, like the long-necked sauropods, maintained rapid growth for much of their lives, reaching their enormous sizes in just a few decades. Others, such as some of the smaller theropods, had growth rates more comparable to those of modern mammals. This rapid growth likely gave dinosaurs a significant advantage in their ecosystems, allowing them to quickly outgrow potential predators and compete more effectively for resources. It also suggests that dinosaurs had metabolisms more similar to warm-blooded animals than to cold-blooded reptiles, further supporting the evolutionary link between dinosaurs and modern birds. Fossilized dinosaur embryos provide a rare and invaluable window into the early stages of dinosaur development. These precious specimens allow paleontologists to study how dinosaurs grew and changed from their earliest moments, offering insights that adult fossils simply cannot provide. By examining the structure and arrangement of bones in fossilized embryos, scientists can determine how quickly different body parts developed and in what order. This information helps reconstruct the growth patterns of various dinosaur species, revealing whether they hatched as relatively mature, ready to fend for themselves, or if they required extensive parental care. Embryonic fossils also shed light on the evolution of certain dinosaur features. For instance, studies of embryonic theropod dinosaurs have shown that some of the characteristics we associate with birds, such as wishbones and three-fingered hands, were present before hatching. This reinforces the evolutionary link between dinosaurs and modern birds. Furthermore, fossilized dinosaur eggs and the embryos within them can provide clues about dinosaur reproductive behaviors. The arrangement of eggs in nests, their size, and the stage of development of the embryos when fossilized all contribute to our understanding of how dinosaurs laid eggs, tended to their young, and potentially lived in family groups or colonies. Dinosaur reproductive strategies were diverse and fascinating, reflecting the wide variety of species that existed during their reign. Large sauropods like Diplodocus likely laid numerous eggs in shallow pits, relying on sheer numbers for species survival. These massive creatures probably provided minimal parental care, leaving their offspring to fend for themselves once hatched. In contrast, smaller theropods such as Oviraptor showed more complex behaviors. Evidence suggests they sat on their nests, protecting and possibly even incubating their eggs. This level of parental investment indicates a strategy focused on fewer but better cared for offspring. Some dinosaurs, like Maiasaura, took parental care even further. Fossil evidence points to these hadrosaurs feeding and protecting their young in the nest for an extended period. This strategy allowed for more developed offspring with a higher survival rate. Interestingly, recent studies suggest that some dinosaurs, particularly among the theropods, may have had a mix of precocial and altricial young in the same clutch. This means some hatchlings were ready to leave the nest quickly, while others required extended care, potentially balancing the benefits of both strategies. The largest known dinosaur egg belonged to a group of long-necked plant-eating dinosaurs called titanosaurs. These eggs, discovered in Argentina, measure about 17 to 20 inches in length and 13 to 15 inches in width. To put this into perspective, they are roughly the size of a medium beach ball or a large watermelon. Despite their impressive size, these eggs are actually smaller than one might expect, given the enormous size of adult titanosaurs. Some of these dinosaurs grew to be longer than 100 feet and weighed as much as 80 tons. The relatively small size of their eggs compared to their adult bodies suggests that titanosaur hatchlings must have experienced incredibly rapid growth rates to reach their massive adult sizes. Interestingly, the shells of these eggs were unusually thin for their size, measuring only about 0.04 to 0.08 inches thick. Scientists believe this adaptation allowed better gas exchange for the developing embryo and made it easier for the hatchlings to break out of the egg. The discovery of these eggs has provided valuable insights into the reproductive strategies and early life of some of the largest animals ever to walk the earth. Dinosaurs' reproductive strategies played a crucial role in their rise to dominance during the Mesozoic era. These ancient reptiles employed a variety of methods to ensure their offspring's survival, which ultimately contributed to their long-lasting reign on Earth. One key factor was the sheer number of eggs many dinosaur species laid. Some large sauropods, for instance, could lay up to 100 eggs in a single clutch. This approach increased the chances that at least some offspring would survive to adulthood, even in the face of predation and harsh environmental conditions. Dinosaurs also exhibited parental care, a trait that significantly boosted their reproductive success. Many species, particularly among the theropods, built nests and guarded their eggs. Some even cared for their young after hatching, providing food and protection during the vulnerable early stages of life. This behavior enhanced the survival rates of offspring and allowed for the passing on of crucial survival skills. Furthermore, dinosaurs' diverse reproductive strategies allowed them to adapt to various ecological niches. From the massive egg-laying colonies of some species to the more intimate family groups of others, dinosaurs developed methods suited to their specific environments and lifestyles. This adaptability enabled them to thrive across different habitats and changing climatic conditions, cementing their dominance for over 160 million years. Growth rings in dinosaur bones offer paleontologists a fascinating window into the life history of these ancient creatures. Similar to the rings found in tree trunks, these concentric layers within fossilized bones provide valuable information about a dinosaur's growth rate, age, and even environmental conditions during its lifetime. These growth rings, also known as lines of arrested growth, form as a result of seasonal changes in the rate of bone deposition. During periods of abundant food and favorable conditions, dinosaurs grew rapidly, creating wide, well-defined rings. Conversely, during times of scarcity or environmental stress, growth slowed, resulting in narrower, more closely spaced rings. By analyzing these patterns, scientists can determine how quickly a dinosaur grew, estimate its age at death, and even identify periods of illness or food scarcity. For instance, studies of Tyrannosaurus rex bones have revealed that these fearsome predators experienced a massive growth spurt during their teenage years, gaining up to 1,400 pounds per year. Furthermore, growth rings can provide insights into dinosaur behavior and ecology. Some species show consistent annual growth patterns, suggesting they lived in stable environments, while others display more erratic growth, indicating adaptability to changing conditions. This information helps paleontologists piece together a more complete picture of dinosaur lives and the prehistoric world they inhabited. The most widely accepted theory for dinosaur extinction is the impact event hypothesis. This theory proposes that a massive asteroid, estimated to be about 10 kilometers in diameter, struck Earth approximately 66 million years ago. The collision site, known as the Chicxulub crater, is located on the Yucatan Peninsula in Mexico. When this enormous space rock hit our planet, it unleashed a catastrophic chain of events. The impact vaporized rock and released an immense amount of dust and debris into the atmosphere. This material blocked out sunlight for an extended period, leading to a rapid and severe global cooling. Plants, which form the base of the food chain, could not photosynthesize effectively in these conditions, causing widespread ecosystem collapse. The impact also triggered massive wildfires, tsunamis, and earthquakes. These events, combined with the prolonged darkness and cooling, created an environment that most large animals, including the dinosaurs, could not survive. Only smaller, more adaptable creatures managed to endure these harsh conditions. Evidence supporting this theory includes a global layer of sediment from this time period containing high levels of iridium, an element rare on Earth but common in asteroids. Additionally, fossil records show a mass extinction event coinciding with this impact, affecting not only dinosaurs but also many other species across the planet. The asteroid impact theory for the extinction of dinosaurs is supported by several compelling lines of evidence. A key piece is the discovery of a thin layer of iridium-rich clay at the boundary between the Cretaceous and Paleogene periods in rock formations worldwide. Iridium is rare on Earth's surface, but common in asteroids, suggesting an extraterrestrial origin for this layer. Researchers have also identified the Chicxulub crater on the Yucatan Peninsula in Mexico, which dates to the time of the extinction event. This massive crater, measuring about 180 kilometers in diameter, matches the size and age predicted by the impact theory. Studies of the crater have revealed shocked quartz and other minerals that form only under intense pressure, consistent with a large asteroid strike. Fossil evidence further supports this theory. The fossil record shows a sudden and widespread extinction of many species at the end of the Cretaceous period, including dinosaurs, marine reptiles, and many plant species. This abrupt change in biodiversity aligns with the catastrophic effects expected from a major asteroid impact. Additionally, computer models have demonstrated how such an impact could have caused global climate changes, including a prolonged period of darkness and cooling due to dust and aerosols in the atmosphere. These conditions would have disrupted photosynthesis and food chains, leading to the observed pattern of extinctions. The Deccan Traps volcanism played a significant role in the extinction of the dinosaurs, though its impact is often overshadowed by the more dramatic asteroid impact. This massive volcanic eruption occurred in what is now India, beginning around 66 million years ago and lasting for nearly a million years. The scale of the Deccan Traps eruption was immense, covering an area larger than modern-day France with thick layers of lava. As the volcanoes erupted, they released enormous amounts of greenhouse gases, including carbon dioxide and sulfur dioxide, into the atmosphere. These gases had a profound effect on the global climate, leading to periods of intense warming followed by cooling. This climate instability put tremendous stress on ecosystems worldwide. Plants struggled to adapt to the rapidly changing conditions, which in turn affected the herbivorous dinosaurs that depended on them for food. The knock-on effect moved up the food chain, impacting carnivorous dinosaurs as well. The volcanic gases also led to acid rain, which further damaged plant life and acidified the oceans, causing problems for marine life. While the Deccan Traps eruption alone might not have been enough to cause a mass extinction, it weakened ecosystems globally. This made life on Earth much more vulnerable to the catastrophic asteroid impact that occurred around the same time, delivering the final blow to the dinosaurs and many other species. The combination of these two major events created the perfect storm for a mass extinction, fundamentally reshaping life on our planet. While the asteroid impact is widely accepted as the primary cause of the dinosaurs' extinction, several other factors likely contributed to their demise. Climate change was already underway before the impact, with global temperatures cooling and sea levels falling. This gradual shift was altering ecosystems and putting pressure on many species. Massive volcanic eruptions in what is now India, known as the Deccan Traps, were also occurring around this time. These eruptions released enormous amounts of greenhouse gases and sulfur dioxide into the atmosphere, further disrupting global climate patterns and potentially poisoning the air and water. The combination of these factors may have weakened dinosaur populations, making them more vulnerable to the catastrophic effects of the asteroid impact. Some scientists suggest that dinosaurs were already in decline due to these environmental stresses, and the impact delivered the final blow. Additionally, the rise of flowering plants and the evolution of new mammal species were changing the dynamics of ecosystems. These shifts may have further challenged the dinosaurs' ability to adapt and survive in a rapidly changing world, ultimately contributing to their extinction alongside the more dramatic events of the time. The end of the dinosaurs' reign was marked by a catastrophic event 66 million years ago, when a massive asteroid struck the Earth. This impact triggered global climate changes, including widespread fires, acid rain, and a prolonged period of darkness and cooling. While this event spelled doom for most dinosaurs, some animals managed to survive and even thrive in its aftermath. The survivors shared several key traits that gave them an edge in the post-impact world. Many were small, allowing them to hide in burrows or crevices, shielding them from the immediate effects of the impact and subsequent environmental changes. These smaller creatures also required less food, making it easier to survive when plant life was scarce. Adaptability played a crucial role as well. Animals with diverse diets or the ability to hibernate had better chances of enduring food shortages. For instance, early mammals, birds, and crocodilians were among the survivors, partly due to their varied eating habits and ability to adapt to changing conditions. Importantly, not all dinosaurs perished. The ancestors of modern birds, which were small, feathered dinosaurs, survived the extinction event. Their ability to fly likely helped them escape local disasters and find new food sources, while their warm-blooded metabolism allowed them to regulate their body temperature in the changing climate. This survival showcases how certain dinosaur traits evolved into advantages that persist to this day in their avian descendants. The extinction event that marked the end of the Cretaceous period and wiped out the dinosaurs was remarkably swift in geological terms. Evidence suggests the main impact and its immediate aftermath unfolded over a matter of days to months. The asteroid, estimated to be about 10 kilometers wide, slammed into Earth with devastating force, unleashing the energy equivalent of over 1 billion atomic bombs. In the hours following impact, a global firestorm likely swept across much of the planet as superheated debris rained back down from the sky. This was followed by massive tsunamis, widespread wildfires, and a choking cloud of dust and aerosols that blocked out the sun. The initial catastrophic phase lasted only days or weeks, but its effects lingered for years. The longer-term environmental consequences, including global cooling and disrupted food chains, persisted for decades to centuries. However, the most intense period of extinction probably occurred within the first few years after impact. This rapid and severe change in Earth's climate and ecosystems led to the extinction of approximately 75% of plant and animal species on the planet. The speed of this extinction event stands in stark contrast to other mass extinctions in Earth's history, which often took place over thousands or even millions of years. This rapid collapse of ecosystems worldwide highlights the devastating potential of sudden, large-scale environmental changes. In the wake of the devastating asteroid impact, Earth transformed into a hellish landscape. Massive wildfires raged across continents, ignited by the intense heat of debris raining down from the sky. The atmosphere filled with thick, choking smoke and dust, blocking out the sun and plunging the planet into a prolonged period of darkness and cold. The initial blast obliterated all life within hundreds of miles of the impact site. Powerful earthquakes shook the ground, triggering tsunamis that swept across coastlines and flooded vast areas of land. Acid rain fell from the skies, poisoning water sources and scorching vegetation that had survived the initial catastrophe. As the dust settled, a profound silence fell over much of the planet. Where once diverse ecosystems thrived, now lay barren wastelands. The few surviving animals faced a harsh new reality, struggling to find food and shelter in a radically altered world. Plants withered in the darkness, unable to photosynthesize, leading to widespread ecosystem collapse. This period of devastation lasted for months, possibly years, as Earth slowly began to recover from the cataclysm. The extinction event had reset the ecological clock, paving the way for new forms of life to emerge and adapt to the changed planet. It marked the end of the age of dinosaurs and the beginning of a new chapter in Earth's history. The extinction of dinosaurs marked a pivotal moment in Earth's history, setting the stage for the rise and diversification of mammals. This catastrophic event, triggered by an asteroid impact approximately 66 million years ago, wiped out about 75% of plant and animal species on our planet. The disappearance of large dinosaurs created numerous ecological niches that were suddenly vacant. In the aftermath of this mass extinction, mammals found themselves in a world with reduced competition and abundant resources. Previously confined to small nocturnal roles, mammals now had the opportunity to explore and adapt to a wide range of environments. This freedom allowed for rapid diversification and evolution of mammalian species. The absence of large predatory dinosaurs meant that mammals could grow larger and occupy more diverse habitats. They evolved to fill roles previously dominated by dinosaurs, from small insectivores to large herbivores and apex predators. This adaptive radiation led to the development of various mammalian forms, including our own primate ancestors. The extinction event also altered the plant life on Earth, with flowering plants becoming more prevalent. This shift in vegetation provided new food sources and habitats for evolving mammals, further driving their diversification. The mammalian ability to regulate body temperature and give birth to live young proved advantageous in this changing world, allowing them to thrive and eventually dominate terrestrial ecosystems. The sudden extinction theory, which proposes that dinosaurs and many other species vanished abruptly due to a catastrophic event, faces several challenges from scientific evidence. Fossil records from the late Cretaceous period show a gradual decline in dinosaur diversity over millions of years before their final disappearance. This slow decrease suggests that dinosaurs were already struggling to adapt to changing environments long before any sudden catastrophe. Additionally, studies of plant fossils and pollen samples indicate a gradual shift in vegetation types leading up to the end of the Cretaceous. This change in plant life would have affected herbivorous dinosaurs first, followed by their carnivorous predators, supporting a more drawn-out extinction process. Climate data from this period also points to long-term cooling trends and sea level changes that could have stressed dinosaur populations over extended periods. These environmental shifts likely made some species more vulnerable to extinction rather than a single, sudden event wiping them out all at once. Furthermore, some dinosaur lineages appear to have survived for a short time after the proposed impact event at the end of the Cretaceous. Fossils found in layers just above the iridium-rich clay associated with the impact suggest that certain dinosaur species persisted for some time, contradicting the idea of an instantaneous, global extinction. Scientists continually refine our understanding of the extinction event through a combination of advanced technologies and interdisciplinary research. New geological evidence is uncovered through improved drilling techniques, allowing researchers to extract and analyze rock samples from the time of the impact. These samples provide crucial information about the environmental conditions before, during, and after the catastrophe. Paleontologists contribute by discovering and studying fossil remains, helping to build a more detailed picture of the species that vanished and those that survived. This work is enhanced by sophisticated dating methods and chemical analysis, which reveal the age and composition of fossils and surrounding sediments with increasing precision. Computer modeling has become an invaluable tool in reconstructing the extinction event. Scientists use powerful simulations to test hypotheses about the impact's effects, from global climate changes to the spread of wildfires and tsunamis. These models are constantly refined as new data becomes available, allowing researchers to better understand the complex chain of events that led to mass extinction. Collaboration across scientific disciplines is key to advancing our knowledge. Geologists, biologists, climatologists, and astrophysicists work together, sharing insights and methodologies. This cross-pollination of ideas leads to new hypotheses and innovative approaches to testing them, gradually building a more comprehensive and accurate picture of one of the most significant events in Earth's history. Dinosaur fossils come in several fascinating forms, each offering unique insights into prehistoric life. Bones and teeth are the most common and recognizable fossils. These hardened remains provide crucial information about a dinosaur's size, structure, and diet. Paleontologists can often identify specific species from a single distinctive bone or tooth. Trace fossils are another important category, which includes footprints, trackways, and even coprolites, or fossilized dung. These preserved traces of dinosaur activity offer valuable clues about behavior, movement patterns, and dietary habits. Dinosaur eggs and nests have also been discovered, sometimes with embryos inside, revealing information about reproduction and growth. Skin impressions and feather imprints are rarer but incredibly informative fossils. These delicate traces provide evidence of dinosaurs' external appearance and have revolutionized our understanding of their relationship to modern birds. In exceptional cases, scientists have found soft tissue remains, including blood vessels and proteins, which offer unprecedented insights into dinosaur biology. Lastly, there are controversial fossils known as mummified dinosaurs. These extremely rare specimens preserve skin, muscles, and organs in addition to bones. While such fossils are exceptionally scarce, they provide an unparalleled glimpse into the actual appearance and internal structure of these ancient creatures. Paleontologists employ meticulous techniques to unearth dinosaur fossils. The process begins with careful prospecting as scientists search for exposed bone fragments on the surface. Once a promising site is identified, they use a variety of tools ranging from small brushes and dental picks for delicate work to larger shovels and even heavy machinery for removing overburden. Excavation is a slow, methodical process. Paleontologists carefully remove layers of rock and sediment, documenting the position and orientation of each fossil as it's exposed. They often apply a hardening solution to fragile bones to prevent crumbling during extraction. Large fossils are encased in protective jackets made of plaster and burlap before being lifted from the ground. Throughout the dig, detailed notes, photographs, and maps are created to record the exact location and context of each find. This information is crucial for understanding the environment in which the dinosaur lived and died. Excavation sites can be vast, sometimes covering hundreds of square meters, and may take years to fully explore. The fossils are then transported to laboratories where they undergo further preparation and study. This entire process, from discovery to analysis, can span decades, requiring immense patience and dedication from the paleontologists involved. Their work continues to unveil the fascinating world of dinosaurs that existed millions of years ago. Scientists employ several sophisticated methods to determine the age of dinosaur fossils. One of the most common techniques is radiometric dating, which measures the decay of radioactive isotopes in the rocks surrounding the fossils. Potassium-40 argon dating is particularly useful for dinosaur fossils, as it can accurately measure ages up to billions of years old. This method relies on the decay of potassium-40 into argon-40, providing a reliable clock for ancient remains. Another valuable tool is biostratigraphy, where researchers analyze the layers of rock in which fossils are found. By studying the succession of fossil species in these layers, scientists can establish relative ages and create a timeline of prehistoric life. This technique is often used in conjunction with radiometric dating to provide a more comprehensive picture of when a dinosaur lived. Magnetostratigraphy offers yet another approach to fossil dating. This method examines the Earth's magnetic field patterns preserved in rocks, which have reverse polarity at known intervals throughout history. By matching these patterns to established timelines, researchers can estimate the age of fossils within the rock layers. For more recent fossils, carbon-14 dating can be applied to any remaining organic material. However, this method is limited to specimens less than 50,000 years old, making it less useful for most dinosaur fossils. These various dating techniques, when used in combination, allow paleontologists to piece together an increasingly accurate timeline of dinosaur evolution and extinction. Scientists employ a range of techniques to reconstruct dinosaur appearances from fossil remains. The process begins with a detailed examination of the bones themselves, which provide crucial information about the animal's size, shape, and structure. Paleontologists study muscle attachment points on the bones to infer the dinosaur's musculature and overall body form. Fossilized skin impressions, when available, offer valuable insights into the texture and patterns of a dinosaur's outer covering. These rare finds can reveal whether the creature had scales, feathers, or other types of skin. In some exceptional cases, fossilized pigment cells have been discovered, allowing scientists to determine the actual colors of certain dinosaurs. Comparisons with modern animals also play a significant role in reconstructing dinosaur appearances. By studying the anatomy and lifestyles of living creatures, particularly birds and reptiles, scientists can make informed estimates about the soft tissues, behavior, and habitat preferences of extinct dinosaurs. This comparative approach helps fill in gaps where fossil evidence is lacking. Advanced technology has revolutionized dinosaur reconstruction in recent years. Computer modeling and three-dimensional scanning techniques allow researchers to create detailed digital models of dinosaur skeletons. These models can then be used to simulate movement, test theories about posture and locomotion, and generate lifelike visual representations of how these ancient creatures might have appeared in their prime. Several remarkable dinosaur fossils have been unearthed over the years, offering unprecedented insights into these ancient creatures. One of the most famous is Sioux, a Tyrannosaurus rex discovered in South Dakota in 1990. Sioux is over 90% complete, providing paleontologists with a wealth of information about the anatomy and life of this fearsome predator. Another extraordinary find is Leonardo, a Brachylophosaurus discovered in Montana. This duck-billed dinosaur is not just a skeleton, but a mummified specimen with preserved skin, scales, and even some internal organs. Such soft tissue preservation is extremely rare and has allowed scientists to study dinosaur biology in remarkable detail. In China, the fossil beds of Liaoning province have yielded numerous exquisitely preserved specimens, including many feathered dinosaurs. One standout is Sinosauropteryx, the first dinosaur found with clear evidence of feathers. This small predator was preserved so perfectly that even its color patterns could be determined. The Borealopelta markmicheli, a nodosaur found in Alberta, Canada, is another astonishing discovery. This armored dinosaur was preserved in 3 dimensions, with its skin, armor, and even stomach contents intact. Such finds are revolutionizing our understanding of dinosaur appearance, behavior, and ecology, bringing these long extinct animals vividly to life in ways previously thought impossible. Fossil formation is a rare and fascinating process that unfolds over millions of years. When an organism dies, its soft tissues typically decay rapidly, leaving behind only the hard parts like bones, shells, or teeth. For fossilization to occur, these remains must be quickly buried by sediment, such as sand or mud, which protects them from scavengers and environmental damage. Over time, minerals from the surrounding sediment slowly replace the original organic material in a process called permineralization. This creates a rock-like copy of the original remains, preserving the organism's structure in remarkable detail. In some cases, the entire organism can be replaced by minerals, forming a cast of its body. Not all environments are conducive to fossil formation. The best conditions are found in areas where sediment accumulates rapidly, such as river deltas, lake beds, or the ocean floor. This is why marine organisms are more commonly found as fossils than land-dwelling creatures. The rarity of fossil formation makes each discovery incredibly valuable to scientists. These preserved remnants of ancient life provide crucial insights into the history of life on Earth, allowing us to piece together the evolutionary story of countless species over billions of years. Coprolites offer paleontologists a treasure trove of information about dinosaurs and their ancient ecosystems. These fossilized feces provide direct evidence of dinosaur diets, shedding light on what these prehistoric creatures consumed millions of years ago. By examining the contents of coprolites, scientists can identify plant material, bone fragments, and even undigested insects, revealing whether a dinosaur was herbivorous, carnivorous, or omnivorous. Beyond diet, coprolites also offer insights into dinosaur digestive systems and overall health. The presence of parasites or unusual substances in the fossilized feces can indicate diseases or environmental stressors affecting dinosaur populations. Furthermore, the shape and size of coprolites can help researchers estimate the body size of the dinosaur that produced them, adding to our understanding of dinosaur physiology and growth patterns. Coprolites also serve as time capsules for ancient ecosystems. Pollen, spores, and small organisms preserved within the fossilized feces provide valuable data about the plants and animals that coexisted with dinosaurs. This information helps scientists reconstruct prehistoric environments and understand the complex relationships between different species in ancient food webs. The study of coprolites extends beyond individual dinosaurs to broader ecological and evolutionary questions. By analyzing coprolites from different time periods and locations, researchers can track changes in dinosaur diets and ecosystems over millions of years. This long-term perspective offers crucial insights into how dinosaurs adapted to changing environments and how their roles in ancient ecosystems evolved throughout the Mesozoic era. Determining the color of dinosaurs was once thought impossible, but recent scientific advancements have opened new doors in paleontology. Researchers now use sophisticated techniques to analyze fossilized pigment cells called melanosomes, which are responsible for color in animals today. These microscopic structures can be preserved in exceptionally well-preserved fossils, particularly in feathers and scales. By comparing the shape, size, and arrangement of these ancient melanosomes to those found in modern animals, scientists can make educated guesses about dinosaur coloration. Another method involves examining trace elements in fossils. Certain chemical signatures can indicate the presence of specific pigments. For instance, copper traces might suggest blue or green hues, while iron could point to reddish tones. While these techniques don't provide a complete color palette for all dinosaurs, they offer fascinating glimpses into the appearance of some species. This research not only helps us visualize extinct creatures more accurately, but also provides insights into dinosaur behavior, habitat preferences, and evolution. Modern technology has revolutionized paleontology, transforming the way scientists study and understand ancient life. Advanced imaging techniques like computed tomography scans allow researchers to peer inside fossils without damaging them, revealing intricate details of bone structure and even preserved soft tissues. This non-invasive approach has led to groundbreaking discoveries about extinct species' anatomy and behavior. Digital modeling and three-dimensional printing have become invaluable tools for paleontologists. By creating accurate replicas of fossils, scientists can manipulate and study specimens without risking damage to irreplaceable originals. These technologies also enable the reconstruction of complete skeletons from fragmentary remains, providing a fuller picture of extinct animals. Satellite imagery and geographic information systems have dramatically improved fossil prospecting. Paleontologists can now identify promising dig sites from afar, saving time and resources. Once in the field, ground-penetrating radar helps locate fossils buried deep underground, while drones survey large areas quickly and efficiently. Genetic analysis has opened up new avenues of research in paleontology. By extracting and sequencing ancient DNA, scientists can now study the evolutionary relationships between extinct and living species with unprecedented accuracy. This molecular approach has shed light on the genetic diversity of past ecosystems and the processes of extinction and adaptation over millions of years. Dinosaur fossils have been discovered on every continent, but certain locations stand out for their remarkable abundance and preservation of prehistoric remains. The Morrison Formation in the western United States is one of the most prolific dinosaur fossil sites, stretching across several states. This rich geological layer has yielded numerous specimens of iconic dinosaurs such as Allosaurus, Stegosaurus, and Diplodocus. In Argentina, the Patagonian region has proven to be a treasure trove of dinosaur fossils. Notable discoveries include some of the largest known dinosaurs, like the massive Patagotitan, as well as remarkably well-preserved eggs and embryos. The area continues to yield new and exciting finds, providing crucial insights into dinosaur evolution and behavior. China has also emerged as a hotspot for dinosaur paleontology, particularly in the Liaoning province. This area is famous for its exquisitely preserved fossils, including many feathered dinosaurs that have revolutionized our understanding of the link between dinosaurs and birds. The fine-grained sediments in this region have preserved even delicate structures like feathers and skin impressions. Another significant site is the Dinosaur Provincial Park in Alberta, Canada. This UNESCO World Heritage Site has produced fossils from over 40 dinosaur species, making it one of the richest dinosaur fossil locales in the world. The park's Badlands topography has exposed layers of sediment deposited during the late Cretaceous period, providing a window into a diverse prehistoric ecosystem. Depictions of dinosaurs in media have undergone a remarkable transformation since their first appearances in popular culture. Early portrayals, dating back to the 19th century, often showed dinosaurs as slow, lumbering creatures dragging their tails on the ground. These images were based on limited scientific knowledge and the assumption that dinosaurs were cold-blooded reptiles similar to modern lizards. As paleontology advanced in the 20th century, our understanding of dinosaurs began to shift. The 1970s saw the beginning of the dinosaur renaissance, a period of intense research and new discoveries. This led to a reimagining of dinosaurs as more active, warm-blooded animals. Media depictions started to show them as faster, more agile, and holding their tails off the ground for balance. The release of Jurassic Park in 1993 marked a significant turning point in dinosaur representation. The film showcased dinosaurs as intelligent, dynamic creatures, capturing the public imagination and influencing subsequent portrayals in movies, television, and books. This new image of dinosaurs as swift, cunning predators or gentle, social herbivores became the standard in popular media. Recent years have seen another shift in dinosaur depictions, driven by new scientific findings. Many dinosaurs are now known to have had feathers, leading to more bird-like representations in documentaries and some films. Additionally, improved understanding of dinosaur behavior and ecosystems has resulted in more nuanced and varied portrayals, showing complex social interactions and diverse adaptations across different species. The Jurassic Park franchise revolutionized public perception of dinosaurs, transforming them from static museum exhibits to dynamic, awe-inspiring creatures. When the first film hit theaters in 1993, it captivated audiences with its groundbreaking special effects and lifelike depictions of these prehistoric animals. The movies popularized the idea of dinosaurs as agile, intelligent beings rather than slow, lumbering reptiles. This shift in perception aligned more closely with emerging scientific theories about dinosaur behavior and physiology. The franchise introduced the public to lesser-known species like Velociraptor, which became a household name despite the films taking liberties with its size and appearance. Jurassic Park also sparked renewed interest in paleontology and dinosaur science. Museum attendance surged, and funding for dinosaur research increased. The films inspired a generation of young people to pursue careers in paleontology and related fields, leading to new discoveries and advancements in our understanding of prehistoric life. However, the franchise also created some misconceptions. Its portrayal of dinosaurs, while exciting, was not always scientifically accurate. For instance, the lack of feathers on many of the depicted theropods contradicted emerging evidence. Despite these inaccuracies, Jurassic Park undeniably brought dinosaurs to life in the public imagination, forever changing how we view these fascinating creatures from Earth's distant past. Dinosaur portrayals in modern documentaries have come a long way, but they still face challenges in achieving complete accuracy. Scientists and filmmakers now collaborate closely to create more realistic depictions based on the latest paleontological evidence. However, there are limitations to our knowledge, and some artistic license is often taken to make the documentaries engaging. One area where accuracy has greatly improved is in the physical appearance of dinosaurs. Modern portrayals often show dinosaurs with feathers, particularly theropods like Velociraptor, reflecting current scientific understanding. Body postures have also been updated, with many dinosaurs now depicted with more horizontal spines rather than the upright, tail-dragging postures of older representations. Behavior and social interactions in documentaries are based on fossil evidence, comparisons with modern animals, and educated speculation. While these portrayals are more informed than in the past, they still involve a degree of uncertainty. Vocalizations, for instance, are often creative interpretations, since we cannot know exactly how dinosaurs sounded. Color and patterning remain largely speculative in most cases. While some fossils have provided clues about certain species' coloration, for many dinosaurs, the colors used in documentaries are educated guesses based on the environments they lived in and the roles color plays in modern animals. Despite these limitations, modern dinosaur documentaries offer a much more scientifically grounded vision of these ancient creatures than ever before. Dinosaurs captivate children's imaginations for several compelling reasons. These ancient creatures, which roamed the Earth millions of years ago, represent a world vastly different from our own, sparking curiosity and wonder. Their immense size, especially when compared to modern animals, leaves a lasting impression on young minds. A Tyrannosaurus rex, for instance, could grow to over 40 feet in length, dwarfing even the largest land animals of today. The diversity of dinosaur species also contributes to their appeal. From the long-necked Brachiosaurus to the three-horned Triceratops, each type of dinosaur offers unique characteristics that children find intriguing. This variety allows young enthusiasts to have favorite dinosaurs, much like they might have favorite characters in stories or shows. Moreover, dinosaurs bridge the gap between reality and fantasy. While they no longer exist, evidence of their presence on Earth is tangible through fossils and museum exhibits. This connection to the real world, combined with the mystery surrounding their extinction, creates a perfect blend of fact and imagination that resonates strongly with children. Lastly, the ongoing discoveries in paleontology keep dinosaurs relevant and exciting. New species are still being unearthed, and our understanding of these prehistoric animals continues to evolve. This constant flow of new information feeds children's natural curiosity and desire to learn, making dinosaurs an enduring source of fascination for young minds. Dinosaur toys have undergone a remarkable transformation over the decades, mirroring the advances in paleontological research and our evolving understanding of these prehistoric creatures. In the early 20th century, dinosaur toys were often depicted as lumbering, slow-moving beasts with dragging tails and upright postures. These representations were based on outdated scientific theories that viewed dinosaurs as cold-blooded and sluggish. As scientific knowledge progressed, so did the accuracy of dinosaur toys. The 1970s saw a shift towards more dynamic and active portrayals, reflecting the growing consensus that many dinosaurs were agile and possibly warm-blooded. Toys began to show dinosaurs with lifted tails and more horizontal body postures, aligning with new fossil evidence and biomechanical studies. The 1990s brought another wave of changes, inspired by groundbreaking discoveries and the popularity of films like Jurassic Park. Toy manufacturers started incorporating feathers on certain dinosaur species, acknowledging the evolutionary link between dinosaurs and birds. This trend has continued, with many modern toys featuring vibrant colors and diverse textures to represent the potential appearance of dinosaur skin and plumage. Today, dinosaur toys strive for scientific accuracy more than ever before. They often include articulated joints to demonstrate range of motion, and come with educational materials explaining current theories about behavior and ecology. From the lumbering behemoths of the past to the diverse, dynamic creatures of modern toys, the evolution of dinosaur playthings reflects our ever-expanding knowledge of these fascinating prehistoric animals. Dinosaur exhibits in museums serve as powerful gateways to science education for people of all ages. These displays bring the ancient world to life, allowing visitors to stand face to face with towering skeletons of creatures that roamed the earth millions of years ago. This tangible connection to prehistory sparks curiosity and wonder, encouraging visitors to ask questions and seek deeper understanding about our planet's past. These exhibits do more than showcase impressive fossils. They provide context for the evolution of life on Earth, helping visitors grasp the vast timescales involved in geological and biological processes. By presenting the latest scientific findings alongside the fossils, museums offer the public access to current paleontological research, bridging the gap between scientific discovery and public knowledge. Dinosaur displays also serve as excellent tools for teaching scientific methods. They demonstrate how paleontologists use evidence from fossils, comparative anatomy, and geological data to reconstruct ancient ecosystems and animal behaviors. This showcases the process of scientific inquiry, helping visitors understand how scientists draw conclusions from available evidence. Moreover, dinosaur exhibits often address current issues like climate change and extinction events. By drawing parallels between past and present, these displays can raise awareness about contemporary environmental challenges, making abstract concepts more relatable and understandable to the general public. Paleontologists in fiction have often been depicted as adventurous and passionate scientists, driven by their curiosity about prehistoric life. These characters frequently appear in novels, films, and television shows, bringing the excitement of fossil hunting and scientific discovery to audiences. One of the most famous fictional paleontologists is Dr. Alan Grant from the Jurassic Park franchise. He embodies the rugged field researcher archetype, combining scientific knowledge with a sense of adventure. This portrayal has influenced public perception of paleontologists as intrepid explorers who uncover the secrets of ancient creatures. In contrast, some works of fiction present paleontologists as more scholarly figures, spending their time in museums and laboratories rather than on excavation sites. These characters often serve as sources of exposition, explaining complex scientific concepts to other characters and the audience. They may be portrayed as socially awkward or eccentric, reinforcing stereotypes about scientists. More recent fictional portrayals have begun to show a diverse range of paleontologists, including women and people of color. These characters challenge traditional stereotypes and reflect the growing diversity in the field of paleontology. They often combine elements of adventure and scholarship, presenting a more nuanced view of the profession. Dinosaur depictions in media often fall short of scientific accuracy, perpetuating misconceptions about these ancient creatures. One common inaccuracy is the portrayal of dinosaurs as cold-blooded, slow-moving reptiles. Modern research suggests that many dinosaurs were likely warm-blooded and quite active, more similar to birds than to crocodiles. Another frequent mistake is the representation of dinosaurs with scaly skin covering their entire bodies. While some dinosaurs did have scales, many species, particularly theropods like Tyrannosaurus rex, likely had feathers or proto-feathers. This feathered appearance is rarely shown in popular media, despite being more scientifically accurate for many species. Size exaggeration is also prevalent in dinosaur depictions. While some dinosaurs were indeed massive, media often portrays them as impossibly large. For instance, Tyrannosaurus rex is sometimes shown towering over buildings, when in reality it stood about 20 feet tall at the hip. Similarly, velociraptors are often depicted as human-sized, when they were actually closer to the size of turkeys. Behavioral inaccuracies abound as well. Dinosaurs are frequently shown roaring like lions, but they likely made sounds more akin to those of modern birds or crocodiles. Additionally, predatory dinosaurs are often portrayed as constantly aggressive, when in reality, like modern predators, they would have spent much of their time resting and conserving energy. These misconceptions, while entertaining, can lead to a skewed understanding of these fascinating prehistoric animals. Dinosaurs have left an indelible mark on modern art and design, captivating creators and audiences alike with their prehistoric allure. These ancient reptiles have inspired countless artists, illustrators, and designers to incorporate their forms and essence into various mediums. In the realm of visual arts, dinosaurs have become iconic subjects for painters and sculptors. Artists often use these extinct creatures to explore themes of power, time, and the relationship between humans and nature. Sculptures of dinosaurs, both realistic and abstract, can be found in museums, public spaces, and private collections worldwide, serving as striking reminders of Earth's distant past. The influence of dinosaurs extends into the world of graphic design and illustration. Their distinctive shapes and features have been stylized and reimagined in logos, mascots, and branding materials. Many companies and organizations, particularly those related to science and education, have embraced dinosaur imagery to convey concepts of strength, longevity, and adaptability. In architecture and interior design, dinosaur-inspired elements add a sense of wonder and playfulness to spaces. From dinosaur-themed children's bedrooms to museum exhibits that recreate prehistoric environments, these designs transport viewers to a long-lost world. The enduring fascination with dinosaurs continues to shape our visual landscape, bridging the gap between ancient history and contemporary creativity. The popularization of dinosaurs has profoundly influenced paleontology, transforming it from a niche scientific discipline into a subject of widespread public fascination. This shift has brought both benefits and challenges to the field. Increased public interest has led to greater funding for paleontological research and expeditions. Museums have seen a surge in visitors, allowing them to expand their exhibits and educational programs. This heightened attention has also inspired a new generation of scientists, with many young people pursuing careers in paleontology and related fields. However, the media portrayal of dinosaurs has sometimes created misconceptions about the nature of paleontological work. The public often expects rapid, dramatic discoveries, while the reality involves meticulous, time-consuming research. Scientists must frequently address and correct popular misconceptions stemming from oversimplified or sensationalized depictions in movies and television. The dinosaur boom has also sparked a problematic market for fossils, with private collectors and commercial entities competing with scientists for important specimens. This has led to ethical debates within the field and efforts to establish guidelines for responsible fossil collection and preservation. Despite these challenges, the overall impact of dinosaur popularization on paleontology has been largely positive, driving scientific progress and public engagement with the fascinating world of prehistoric life. During the age of dinosaurs, the oceans teemed with a diverse array of marine reptiles. These formidable creatures dominated the seas for millions of years, evolving into various specialized forms. The main groups of marine reptiles during this era were the ichthyosaurs, plesiosaurs, and mosasaurs. Ichthyosaurs were among the earliest to appear, emerging in the Triassic period. These streamlined predators resembled modern dolphins in shape, with long snouts filled with sharp teeth and powerful tails for propulsion. They ranged in size from small, meter-long species to giants stretching up to 20 meters in length. Plesiosaurs evolved into two distinct body types. The long-necked varieties, such as elasmosaurs, had small heads atop serpentine necks that could stretch up to 13 meters. In contrast, the short-necked pliosaurs boasted massive skulls and powerful jaws, making them apex predators of their time. Both types used 4 large flippers to navigate through the water with grace and speed. Mosasaurs appeared later, during the Cretaceous period, and quickly became dominant marine predators. These massive lizards, closely related to modern snakes and monitor lizards, grew up to 17 meters long. With their long, streamlined bodies, powerful tails, and jaws lined with sharp teeth, mosasaurs were fierce hunters that fed on a variety of prey, including fish, squid, and even other marine reptiles. Pterosaurs and dinosaurs were distinct groups of reptiles that lived during the Mesozoic era. While both were successful and diverse, they had key differences in their anatomy and lifestyle. Pterosaurs were flying reptiles, the first vertebrates to evolve powered flight. Their wings were formed by a membrane of skin stretched between an elongated fourth finger and their body. This unique wing structure set them apart from both dinosaurs and modern birds. Pterosaurs had hollow bones and a keeled breastbone for flight muscle attachment, adaptations convergent with those of birds but independently evolved. Dinosaurs, on the other hand, were primarily terrestrial animals. While some dinosaurs eventually evolved into birds, most were ground-dwelling creatures. They had a wide range of body plans, from the massive, long-necked sauropods to the agile, bipedal theropods. Dinosaurs had a distinctive hip structure and upright leg posture, allowing for efficient movement on land. Another key difference was their skull structure. Pterosaurs had large brains relative to their body size and often sported elaborate head crests. Dinosaur skulls varied widely, but generally had smaller brain cavities. Despite these differences, both groups were highly successful, dominating their respective niches for millions of years until their extinction at the end of the Cretaceous period. During the age of dinosaurs, mammals were present but lived in the shadows of their giant reptilian counterparts. These early mammals were typically small, nocturnal creatures that occupied specific ecological niches. Many were insectivores, feeding on insects and other small invertebrates, while others developed specialized diets. One group of mammals that coexisted with dinosaurs was the multituberculates. These rodent-like creatures had unique teeth adapted for grinding plant material and insects. They survived for over 120 million years, outlasting the dinosaurs and only going extinct about 35 million years ago. Another notable group was the Morganucodontids, some of the earliest true mammals. These shrew-sized animals likely had fur and warm blood, characteristics that would become hallmarks of later mammals. They possess specialized ear bones that improved their hearing, giving them an advantage in detecting both prey and predators. The monotremes, represented today by the platypus and echidnas, also emerged during the dinosaur era. These egg-laying mammals developed unique features like electroreception, which allowed them to sense electrical impulses from their prey. This adaptation helped them thrive in aquatic environments where many dinosaurs could not compete effectively. Crocodilians and dinosaurs share a fascinating evolutionary history that stretches back over 200 million years. These ancient reptiles emerged during the Triassic period, evolving from a common ancestor with dinosaurs and pterosaurs. While dinosaurs diversified into a wide array of species, crocodilians developed their distinctive body plan early on and have remained relatively unchanged since. The early crocodilians, known as pseudosuchians, were more diverse than their modern counterparts. Some were fully terrestrial and could run on two legs, while others were herbivores. As dinosaurs began to dominate terrestrial ecosystems, crocodilians adapted to aquatic and semi-aquatic niches, developing the powerful swimming tails and armored bodies we recognize today. Throughout the Jurassic and Cretaceous periods, crocodilians continued to evolve alongside dinosaurs, occupying various ecological roles. Some grew to enormous sizes, like Sarcosuchus, which reached lengths of up to 40 feet. These giant crocodilians were apex predators in their environments, potentially competing with large theropod dinosaurs for prey. When the mass extinction event occurred at the end of the Cretaceous period, wiping out non-avian dinosaurs, crocodilians managed to survive. Their semi-aquatic lifestyle and ability to remain submerged for long periods may have helped them weather the catastrophic changes. This resilience allowed crocodilians to persist and thrive, becoming one of the few groups of large reptiles to survive into the modern era alongside the descendants of dinosaurs, birds. During the age of dinosaurs, arthropods reached impressive sizes, dwarfing their modern counterparts. One of the most notable giants was Arthropleura, a relative of modern millipedes and centipedes. This creature could grow up to 2.5 meters in length, making it the largest known land-dwelling arthropod of all time. Imagine a creature longer than a human adult, with numerous legs and a segmented body, crawling through the ancient forests. In the skies, massive dragonfly-like insects known as griffinflies dominated. The largest of these, Meganeuropsis, had a wingspan that stretched up to 70 centimeters. These predatory insects were formidable hunters, their large compound eyes and powerful wings allowing them to chase down smaller flying creatures with ease. The oceans of the Mesozoic era also harbored enormous arthropods. Sea scorpions, or eurypterids, were among the largest. Some species could grow up to 2 meters in length, with powerful pincers and a venomous tail. These aquatic predators were fierce hunters, capable of taking down fish and other marine life. It is worth noting that while these arthropods were indeed large by today's standards, they were not contemporaries of the largest dinosaurs. Many of these giant arthropods lived during the Carboniferous and Permian periods, predating the rise of dinosaurs. However, their existence showcases the potential for arthropods to reach impressive sizes given the right environmental conditions, such as higher oxygen levels in the atmosphere. Early birds, emerging around 150 million years ago, represented a remarkable evolutionary leap from their dinosaur ancestors. These pioneering avians, like Archaeopteryx, retained many features of their theropod dinosaur relatives while developing crucial adaptations for flight. One of the most striking differences was the presence of feathers. While some dinosaurs had feather-like structures, early birds possessed true feathers arranged in a pattern conducive to flight. These feathers were lighter and more complex than their dinosaur precursors, with interlocking barbs that created a smooth aerodynamic surface. The skeletal structure of early birds also underwent significant changes. Their bones became hollow and lightweight, reducing overall body mass. The wishbone, or furcula, became more pronounced, providing essential support for flight muscles. Additionally, early birds developed a keeled breastbone, offering an expanded attachment site for powerful flight muscles. Perhaps most notably, early birds experienced a reduction in size compared to their dinosaur ancestors. This miniaturization allowed for more efficient flight and opened up new ecological niches. Despite these changes, early birds still possessed dinosaur-like features such as teeth and long, bony tails, reminding us of their ancient lineage and the gradual nature of evolution. The Mesozoic era saw a remarkable diversity of plant life, with several groups dominating the landscape. Ferns and their relatives, which had been prevalent since the Paleozoic, continued to thrive in many environments. These ancient plants, with their distinctive fronds and spore-based reproduction, formed lush understories in forests and colonized open areas. Gymnosperms, particularly conifers, became increasingly important during this time. Towering forests of pine-like trees spread across the land, their needle-like leaves well adapted to the changing climate. Cycads, with their stout trunks and crown of large, stiff leaves, were also common, especially in tropical and subtropical regions. One of the most significant developments of the Mesozoic was the emergence and rapid diversification of flowering plants, or angiosperms. Although they appeared relatively late in the era, angiosperms quickly became dominant in many ecosystems. Their ability to form cooperative relationships with insects for pollination gave them a significant advantage. Ginkgos, with their distinctive fan-shaped leaves, were another notable plant group during the Mesozoic. These trees, represented today by a single species, were once far more diverse and widespread. Their resilience allowed them to survive through major extinction events, making them living fossils in our modern world. Turtles emerged during the Triassic period, about 220 million years ago, predating many dinosaur species. Their evolution during the age of dinosaurs was marked by significant adaptations that have allowed them to survive to the present day. The earliest known turtle ancestor, Odontochelys semitestacea, appeared in China during the late Triassic. This ancient species already possessed the characteristic turtle shell, though only on its underside. Over time, turtles developed a full shell, providing crucial protection against predators in a world dominated by fearsome dinosaurs. During the Jurassic period, turtles diversified into various lineages, including land-dwelling and aquatic species. Some grew to enormous sizes, like Archelon, which lived alongside marine reptiles and reached lengths of up to 4 meters. These adaptations allowed turtles to occupy diverse ecological niches, from shallow seas to freshwater environments and terrestrial habitats. By the Cretaceous period, turtles had evolved into forms remarkably similar to those we see today. They developed specialized diets, ranging from plant matter to small animals, and refined their shell structures. This remarkable adaptability ensured their survival through the mass extinction event that wiped out the dinosaurs, allowing turtles to continue their evolutionary journey into the modern era. Synapsids were a diverse group of animals that dominated terrestrial ecosystems long before dinosaurs appeared. These creatures, which include the ancestors of mammals, first emerged around 300 million years ago during the late Carboniferous period. They quickly became the most prevalent and varied land vertebrates, filling numerous ecological niches. In the Permian period, synapsids reached their peak diversity. They ranged from small insectivores to large herbivores and apex predators. Some notable examples include Dimetrodon, a sail-backed carnivore, and Moschops, a heavily built herbivore. These animals played crucial roles in their ecosystems, shaping the landscape and influencing the evolution of other species. As the Permian gave way to the Triassic, synapsids faced significant challenges. The end Permian mass extinction, the largest in Earth's history, wiped out many synapsid lineages. In the early Triassic, the surviving synapsids, mainly smaller species, began to recover and diversify once again. However, they now shared the landscape with the emerging archosaurs, the group that would eventually give rise to dinosaurs. During the rise of dinosaurs in the late Triassic, synapsids were gradually outcompeted in many ecological roles. Yet, they did not disappear entirely. Instead, they adapted to new niches, often becoming smaller and more specialized. These survivors evolved into the first true mammals, setting the stage for their own diverse radiation millions of years later after the extinction of the non-avian dinosaurs. Fish diversity underwent significant changes throughout the Mesozoic era, a time span lasting from about 252 million years ago to 66 million years ago. This era, known for its dominant reptilian life forms, also saw major developments in fish evolution. At the start of the Mesozoic, during the Triassic period, fish populations were recovering from the devastating Permian-Triassic extinction event. This mass extinction had wiped out many ancient fish lineages, creating ecological opportunities for surviving groups. As the Triassic progressed, ray-finned fishes began to diversify and expand their presence in both marine and freshwater environments. The Jurassic period marked a significant turning point for fish diversity. This era saw the rise of teleost fishes, a group that would eventually come to dominate aquatic ecosystems. Teleosts, characterized by their flexible jaws and tail fins, evolved a wide array of body shapes and sizes, allowing them to exploit various ecological niches. Alongside teleosts, cartilaginous fishes like sharks and rays also experienced notable diversification. By the Cretaceous period, the final stage of the Mesozoic, fish diversity had reached new heights. Teleosts had become the dominant group of bony fishes, exhibiting an incredible range of adaptations. This period also saw the emergence of many modern fish groups, setting the stage for the diverse aquatic ecosystems we see today. The end of the Mesozoic, marked by another mass extinction event, would once again reshape fish populations, leading to the dominance of teleosts in the subsequent Cenozoic era. Bipedal dinosaurs evolved remarkable adaptations to balance their bodies effectively. These prehistoric creatures, which walked on two legs, developed a unique skeletal structure that allowed them to maintain stability while moving. The key to their balance lay in the positioning of their center of gravity. Unlike humans, who have an upright posture, bipedal dinosaurs had a horizontal posture with their tails extended behind them. This tail served as a counterbalance to the weight of their body and head. The long, heavy tail shifted their center of gravity towards their hips, aligning it with their leg muscles. This alignment allowed them to stand and move with greater ease and stability. Additionally, many bipedal dinosaurs had a reinforced hip structure and powerful leg muscles. These features provided the strength and support needed to carry their body weight on two legs. Some species also developed a specialized foot structure with 3 forward-facing toes, which helped distribute their weight evenly and provided better traction on various terrains. The ability to balance on 2 legs offered bipedal dinosaurs several advantages. It allowed them to run faster, freed up their forelimbs for other uses, and gave them a higher vantage point to spot predators or prey. This efficient body design contributed to the success and diversity of bipedal dinosaurs throughout their reign on Earth. Determining the running speeds of extinct dinosaurs presents a fascinating challenge for paleontologists. Our understanding comes from a combination of fossil evidence, biomechanical studies, and comparisons with modern animals. Fossilized footprints provide valuable clues about dinosaur locomotion. Trackways, preserved sequences of footprints, allow scientists to calculate stride length and estimate speed. For instance, trackways discovered in Texas suggest that some theropod dinosaurs could reach speeds of up to 25 miles per hour. Skeletal structure also offers insights into potential running abilities. By examining leg bones, muscle attachment sites, and overall body proportions, researchers can make informed estimates about a dinosaur's speed and agility. Computer simulations and three-dimensional modeling have further refined these estimates, taking into account factors like body mass and center of gravity. Comparisons with living animals, particularly birds, which are modern descendants of dinosaurs, provide additional context. Studies of ostrich locomotion, for example, have helped scientists better understand how large, bipedal dinosaurs might have moved. While we cannot know exact speeds with certainty, this multidisciplinary approach gives us a reasonable picture of dinosaur locomotion capabilities. Sauropods, the massive long-necked dinosaurs that roamed the Earth millions of years ago, evolved remarkable adaptations to support their enormous weight. These gentle giants, some weighing as much as 10 adult African elephants, had several key features that allowed them to move and thrive despite their colossal size. One crucial adaptation was their skeletal structure. Sauropod bones were filled with small air sacs, similar to those found in modern birds. This feature significantly reduced the overall weight of their skeleton while maintaining strength. Their vertebrae were also specially designed with complex networks of air chambers and struts, providing a lightweight yet sturdy support system for their long necks and tails. The limbs of sauropods were another engineering marvel. Their legs were columnar, much like those of modern elephants, allowing them to support tremendous weight efficiently. These sturdy limbs were positioned directly under the body, distributing the animal's mass evenly. Additionally, sauropods had large, padded feet that helped spread their weight over a broader area, preventing them from sinking into soft ground. Interestingly, recent studies suggest that sauropods might have had cartilage-filled joints, acting as shock absorbers and reducing stress on their massive frames. This combination of adaptations allowed these incredible creatures to support their immense weight, move with relative ease, and dominate their ecosystems for millions of years. Dinosaur trackways provide invaluable insights into how these ancient creatures moved and behaved. These fossilized footprints, often found in long sequences, reveal much more than just the shape of dinosaur feet. They offer a window into the past, showing us the speed, gait, and even social behavior of dinosaurs. By studying the distance between footprints, scientists can calculate the stride length of different dinosaur species. This information, combined with estimates of leg length based on skeletal remains, allows researchers to determine how fast dinosaurs were moving when they left their tracks. Some trackways show dinosaurs moving at a leisurely walk, while others indicate they were capable of running at considerable speeds. The arrangement of footprints in trackways also tells us about dinosaur posture and gait. For instance, the narrow trackways of some large sauropods suggest these massive creatures walked with a columnar limb posture, much like modern elephants. In contrast, the wider trackways of some theropods indicate a more dynamic gait, with legs positioned under the body for faster, more agile movement. Perhaps most intriguingly, multiple trackways found together can reveal social behaviors. Parallel trackways of similar-sized individuals suggest some dinosaur species moved in herds or family groups. In some cases, trackways have even shown evidence of predator-prey interactions, with the footprints of carnivorous dinosaurs intersecting those of potential prey species, offering a dramatic snapshot of prehistoric life in motion. Dinosaur tails played a crucial role in the locomotion of these ancient creatures, serving multiple functions that varied depending on the species. For many dinosaurs, particularly the large, long-necked sauropods and the bipedal theropods, the tail acted as a counterbalance to the front of the body. This counterbalancing effect was essential for maintaining stability and balance while walking or running. In theropod dinosaurs, such as Tyrannosaurus rex, The muscular tail helped shift the center of gravity backward, allowing them to stand upright on two legs. As these dinosaurs moved, their tails would sway from side to side, providing momentum and aiding in quick direction changes. This tail movement also helped to conserve energy during locomotion, making their movements more efficient. For quadrupedal dinosaurs like Stegosaurus and Ankylosaurus, the tail served as both a counterbalance and a defensive weapon. While walking, their tails would have moved in a sweeping motion, contributing to their overall stability. Some scientists believe that certain dinosaur species may have used their tails as rudders when swimming, though this remains a topic of ongoing research and debate. Recent studies have also suggested that some dinosaurs, particularly smaller, agile species, may have used their tails to generate thrust during running. By swinging their tails up and down, these dinosaurs could have increased their speed and agility, similar to how modern cheetahs use their tails for quick turns and acceleration. Certain dinosaurs evolved remarkable adaptations for life in aquatic environments. The Spinosaurus, a massive carnivore, developed dense bones and paddle-like feet that aided in swimming and maneuvering through water. Its long, crocodile-like snout was perfectly suited for catching fish, while its nostrils were positioned high on its skull, allowing it to breathe while partially submerged. Other dinosaurs, like the duck-billed hadrosaurs, had webbed hands that likely helped them paddle through water. Some paleontologists believe these creatures were skilled swimmers, capable of crossing rivers and lakes with ease. Their powerful tails could have served as effective propulsion mechanisms in aquatic settings. The Nyctosaurus, a type of pterosaur often mistaken for a dinosaur, had uniquely shaped wings that some scientists theorize were adapted for skimming across water surfaces to catch fish. This technique, similar to that of modern seabirds, would have allowed it to feed efficiently in marine environments. These adaptations highlight the diverse ways dinosaurs evolved to exploit aquatic niches, showcasing their remarkable ability to thrive in various environments across the Mesozoic era. As we continue to uncover new fossils and analyze existing specimens, our understanding of dinosaur adaptations for aquatic life continues to grow and evolve. Dinosaur hip structures played a crucial role in shaping their distinctive gaits, influencing how these ancient creatures moved and interacted with their environments. The two main types of hip structures found in dinosaurs were the lizard-hipped and bird-hipped configurations. Lizard-hipped dinosaurs, known as saurischians, had a hip structure that allowed for greater leg mobility. This increased range of motion enabled them to take longer strides and potentially move faster. Theropods, including the famous Tyrannosaurus rex, belonged to this group and often exhibited a more upright posture, with legs positioned directly beneath their bodies. In contrast, bird-hip dinosaurs, or ornithischians, had a hip structure that resulted in a different gait. Their legs were positioned slightly outward from their bodies, creating a wider stance. This arrangement provided more stability, but generally resulted in slower movement compared to their lizard-hipped counterparts. Many herbivorous dinosaurs, such as Stegosaurus and Triceratops, belonged to this group. The differences in hip structures and resulting gaits had significant implications for dinosaur behavior and ecology. Lizard-hipped dinosaurs were often better suited for pursuit and predation, while bird-hipped dinosaurs evolved adaptations that favored defense and efficient plant consumption. These distinct locomotion styles shaped the diverse roles dinosaurs played in their ancient ecosystems. Paleontologists have developed several theories about dinosaur stamina and endurance based on fossil evidence and comparisons with modern animals. One prominent theory suggests that many large dinosaurs, particularly long-necked sauropods, were warm-blooded and capable of sustained activity. This idea is supported by the structure of dinosaur bones, which often show similarities to those of active, endothermic animals like mammals and birds. Another theory focuses on the respiratory systems of dinosaurs. Some scientists believe that certain dinosaurs, especially theropods like Tyrannosaurus rex, had bird-like air sac systems. This efficient breathing mechanism would have allowed for better oxygen uptake, potentially enabling higher levels of stamina and endurance during physical activities such as hunting or long-distance travel. The shape and arrangement of dinosaur leg bones have also led to theories about their endurance capabilities. Some studies suggest that certain dinosaurs, particularly ornithopods like iguanodon, had leg structures well suited for efficient, sustained movement. This adaptation might have allowed them to cover large distances in search of food or to escape predators. However, not all dinosaurs are thought to have been built for endurance. Some theories propose that heavily armored dinosaurs, such as ankylosaurs and stegosaurs, may have had lower stamina due to their body mass and the energy required to move their protective plates and spikes. These dinosaurs might have relied more on short bursts of activity rather than prolonged exertion. Dinosaur foot structure exhibited remarkable diversity across different species, reflecting their varied lifestyles and environments. Theropods, the group including famous carnivores like Tyrannosaurus rex, typically had 3 forward-facing toes with sharp claws, ideal for gripping prey and maintaining balance while running. These feet were often narrow and elongated, allowing for swift movement and agile hunting. In contrast, large herbivorous sauropods like Brachiosaurus had feet more reminiscent of modern elephants. Their feet were broad and flat, with 5 toes arranged in a semicircular pattern. This structure helped distribute their immense weight over a larger surface area, preventing them from sinking into soft ground. Ornithischian dinosaurs, such as Stegosaurus and Triceratops, displayed yet another foot type. Many had 4 or 5 weight-bearing toes, with some species possessing hoof-like structures on their toes. This adaptation was particularly useful for traversing varied terrain and supporting their bulky bodies. Some dinosaurs even developed specialized foot structures for specific purposes. Deinonychosaurs, close relatives of birds, had a distinctive sickle-shaped claw on their second toe, which they could raise off the ground while walking. This feature likely aided in hunting and climbing, showcasing how foot structure could evolve for highly specialized functions in different dinosaur lineages. Biomechanical studies have revolutionized our understanding of dinosaur movement, shedding light on how these ancient creatures walked, ran, and interacted with their environment. By analyzing fossilized bones, tracks, and using advanced computer modeling, scientists have uncovered fascinating insights into dinosaur locomotion. One key discovery is that many large dinosaurs, such as Tyrannosaurus rex, likely moved more slowly than previously thought. Contrary to popular depictions in movies, these massive predators probably had a top speed of around 12 miles per hour. This finding is based on studies of muscle attachment points, bone strength, and the creature's overall body mass. Research has also revealed that some dinosaurs, particularly long-necked sauropods, may have been more agile than their size suggests. Computer simulations have shown that despite their enormous bulk, these giants could potentially have reared up on their hind legs to reach high vegetation or defend themselves. This challenges the old notion of sauropods as lumbering, slow-moving animals. Biomechanical analysis of dinosaur tails has provided insights into balance and movement. Many theropod dinosaurs, like Velociraptor, use their tails as counterbalances when running, allowing for quick turns and agile movements. This understanding has reshaped our view of how these predators hunted and interacted with their prey. Dinosaur vision has been a fascinating subject of study for paleontologists and evolutionary biologists. Through careful examination of fossil evidence and comparisons with modern animals, scientists have pieced together intriguing insights into how these ancient creatures perceived their world. Many dinosaurs, particularly the predatory species, likely had excellent vision. Skull fossils reveal large eye sockets, suggesting they had big eyes capable of gathering lots of light. This would have been crucial for hunting, especially for those that may have been active at dawn, dusk, or even at night. Some scientists believe that certain dinosaurs, like the Tyrannosaurus rex, might have had vision as sharp as that of modern-day hawks or eagles. Color vision was probably a feature for many dinosaurs, especially among the smaller bird-like species. This conclusion is based on the presence of specific eye structures found in well-preserved fossils. Color vision would have been advantageous for identifying potential mates, recognizing different species, and spotting colorful fruits or flowers for herbivorous dinosaurs. Interestingly, some dinosaurs may have had enhanced depth perception due to the positioning of their eyes. Predatory dinosaurs often had forward-facing eyes, providing binocular vision similar to modern predators. This arrangement allows for better judgment of distances, which would have been crucial when chasing prey or navigating through complex environments. Dinosaur hearing was quite different from that of many modern animals, reflecting their unique evolutionary path and the environments they inhabited. By studying fossilized skulls and inner ear structures, scientists have gained insights into how these ancient creatures perceived sound. Many dinosaurs, especially larger species like Tyrannosaurus rex, had hearing ranges that focused on low-frequency sounds. This adaptation allowed them to detect the footsteps and vocalizations of other large dinosaurs from considerable distances. In contrast, most mammals today, including humans, have a broader range of hearing that includes higher frequencies. Interestingly, some dinosaurs, particularly smaller species and those related to modern birds, developed more sophisticated hearing abilities. These creatures could likely detect a wider range of frequencies, similar to contemporary birds. This enhanced hearing would have been crucial for communication, detecting predators, and locating prey in dense forest environments. Comparing dinosaur hearing to that of their closest living relatives, crocodiles and birds, provides further insights. Crocodiles, like many dinosaurs, are sensitive to low-frequency sounds, while birds have evolved to hear higher frequencies. This suggests that dinosaur hearing likely fell somewhere between these two extremes, with variations across different species and families. Paleontologists have uncovered fascinating evidence about dinosaur olfactory abilities through careful study of fossilized skulls. By examining the olfactory bulbs and nasal cavities of various dinosaur species, scientists have gained insights into their sense of smell. One key piece of evidence comes from the discovery of well-preserved skulls belonging to Tyrannosaurus rex. These fossils reveal that T. rex had exceptionally large olfactory bulbs relative to its brain size, suggesting a highly developed sense of smell. This powerful olfactory capability likely aided T. rex in hunting and locating prey over long distances. Other dinosaur species also show adaptations for enhanced smell. Herbivorous dinosaurs like Stegosaurus and Triceratops had complex nasal passages that may have helped them detect predators or locate food sources. Some scientists propose that the long snouts of sauropods, such as Brachiosaurus, could have housed intricate olfactory structures, potentially allowing these massive creatures to navigate their environment and find suitable vegetation. Recent advancements in imaging technology have allowed researchers to create detailed three-dimensional models of dinosaur skulls, providing even more accurate assessments of their olfactory capabilities. These studies continue to refine our understanding of how different dinosaur species used their sense of smell to survive and thrive in their ancient ecosystems. Dinosaurs possessed remarkable balance and spatial awareness, crucial for their survival in prehistoric environments. These abilities were governed by complex systems within their bodies, much like those found in modern animals. The vestibular system, located in the inner ear, played a vital role in dinosaur balance. This intricate network of fluid-filled canals and sensory organs detected head movements and changes in body position. For large dinosaurs like Tyrannosaurus rex, this system was particularly important, allowing them to maintain stability despite their massive size. Dinosaurs also relied on proprioception, the sense of body position and movement. Specialized receptors in their muscles, tendons, and joints provided constant feedback about limb positions and body orientation. This information, combined with visual cues, allowed dinosaurs to navigate their surroundings effectively. Interestingly, some dinosaurs developed additional adaptations for enhanced spatial awareness. Certain species, like the duck-billed hadrosaurs, had enlarged optic lobes in their brains, suggesting highly developed vision. This keen eyesight likely improved their ability to perceive depth and judge distances, further refining their spatial awareness in diverse prehistoric landscapes. Aquatic dinosaurs developed remarkable sensory adaptations to thrive in their watery environments. These creatures, such as the plesiosaurs and ichthyosaurs, evolved specialized features to navigate, hunt, and survive beneath the waves of ancient seas. One key adaptation was enhanced vision. Many aquatic dinosaurs had large eyes with reinforced scleral rings, allowing them to see clearly underwater and in low-light conditions. This improved eyesight was crucial for detecting prey and avoiding predators in the murky depths. Their sense of hearing also underwent significant changes. Some species developed structures similar to those found in modern whales and dolphins, enabling them to use echolocation. This ability allowed them to navigate and locate prey by producing high-frequency sounds and interpreting the echoes. Additionally, these marine reptiles likely possessed highly sensitive pressure receptors along their bodies, similar to the lateral line system in fish. This adaptation would have helped them detect minute changes in water pressure, alerting them to nearby movements and aiding in spatial awareness as they maneuvered through their aquatic habitats. Dinosaur brains, like those of modern reptiles and birds, had specialized regions for processing different types of sensory information. The olfactory bulbs, responsible for smell, were often well developed in many dinosaur species, suggesting a keen sense of smell. This was particularly important for predators like Tyrannosaurus rex, which likely used its powerful sense of smell to locate prey and potential mates. The optic lobes, which process visual information, were also significant in many dinosaur species, especially in predatory theropods. These enlarged optic lobes indicate that vision played a crucial role in their daily lives, whether for hunting, avoiding predators, or navigating their environment. Some dinosaurs, like the small bird-like Troodon, had particularly large optic lobes, suggesting highly developed visual capabilities. The cerebellum, responsible for motor control and balance, was well developed in many dinosaur species, especially in bipedal theropods. This adaptation allowed for precise movements and coordination, essential for both predators and prey. The enlarged cerebellum in some species also hints at complex behaviors and possibly even social interactions. While our understanding of dinosaur brains is limited by the fossil record, studies of brain casts and comparisons with modern relatives provide valuable insights into how these ancient creatures processed sensory information. The diversity of brain structures among different dinosaur groups reflects their varied lifestyles and adaptations to different ecological niches throughout the Mesozoic era. Touch played a crucial role in the lives of dinosaurs, serving as a vital sense for interacting with their environment and each other. Dinosaurs possessed an array of touch receptors in their skin, allowing them to perceive physical contact, pressure, and temperature changes. These sensory capabilities were essential for various aspects of their daily lives, from navigation to social interactions. For many dinosaur species, touch was particularly important during mating rituals and courtship behaviors. Some dinosaurs likely used gentle nuzzling or rubbing against potential mates as part of their courtship displays. Additionally, touch was crucial for parental care in species that nurtured their young. Fossil evidence suggests that some dinosaurs, such as Maiasaura, cared for their offspring in nests, where touch would have been essential for feeding and protecting their young. Dinosaurs also relied on their sense of touch for foraging and feeding. Herbivorous dinosaurs used their sensitive lips and tongues to distinguish between edible plants and potentially harmful vegetation. Carnivorous dinosaurs, on the other hand, used touch receptors in their snouts and around their teeth to manipulate prey and determine the most efficient way to consume their meals. The sense of touch also played a role in dinosaurs' ability to navigate their surroundings. Many species likely use their tails, limbs, and other body parts to feel their way through dense vegetation or rocky terrain. This tactile feedback would have been especially valuable in low-light conditions or for species with limited vision, helping them avoid obstacles and locate safe paths through their habitats. Nocturnal dinosaurs developed remarkable adaptations to thrive in the darkness of night. Their eyes grew larger and more sensitive, allowing them to gather as much light as possible in low-light conditions. The shape of their eye sockets expanded to accommodate these enlarged eyes, a feature we can observe in fossilized skulls. These night-dwelling dinosaurs also evolved enhanced hearing abilities. Their ear structures became more sophisticated, enabling them to detect the faintest sounds of prey or predators in the dark. Some species developed asymmetrical ears, with one ear positioned slightly higher than the other. This arrangement helped them pinpoint the exact location of sounds more accurately. The sense of smell became increasingly important for nocturnal dinosaurs. Their olfactory bulbs, the parts of the brain responsible for processing scents, grew larger over time. This heightened sense of smell allowed them to track prey, locate food, and navigate their environment using odor cues when visual information was limited. Touch sensors also played a crucial role in their nighttime adaptations. Many nocturnal dinosaurs developed sensitive skin and facial structures, including whisker-like sensory organs. These tactile adaptations helped them feel their way through dark environments and detect subtle air movements, giving them an additional advantage in navigating and hunting under the cover of darkness. The size of dinosaur olfactory bulbs provides valuable insights into their sense of smell. These structures, located in the front of the brain, are responsible for processing scent information. By examining fossilized dinosaur skulls, paleontologists can estimate the size and shape of these olfactory bulbs, offering clues about the importance of smell in different dinosaur species. Generally, larger olfactory bulbs relative to overall brain size indicate a more developed sense of smell. Some predatory dinosaurs, like Tyrannosaurus rex, had proportionally large olfactory bulbs, suggesting they relied heavily on their sense of smell for hunting and navigating their environment. This enhanced olfactory capability likely allowed them to detect prey from considerable distances and potentially track scent trails. In contrast, certain herbivorous dinosaurs had smaller olfactory bulbs, indicating that smell may have played a less crucial role in their daily lives. However, this does not mean their sense of smell was entirely unimportant. Even with smaller olfactory bulbs, these dinosaurs might have used scent to identify suitable food sources or detect the presence of predators. Studying olfactory bulb size across different dinosaur species helps scientists understand how these ancient creatures interacted with their environments and each other. This information contributes to our broader understanding of dinosaur behavior, ecology, and evolution, painting a more complete picture of life in the Mesozoic era. Dinosaurs developed increasingly sophisticated sensory abilities throughout their long reign on Earth. Early dinosaurs from the Triassic period had relatively simple sensory systems with basic sight, hearing, and smell capabilities. As dinosaurs diversified and adapted to various environments, their senses became more refined and specialized. Vision saw significant improvements over time. Many dinosaurs evolved larger eyes and enhanced color perception, allowing them to navigate their surroundings more effectively and spot potential prey or predators from greater distances. Some species, like the Tyrannosaurus rex, developed binocular vision, enabling better depth perception and more precise hunting. Hearing abilities also advanced considerably. Dinosaurs gradually evolved more complex inner ear structures, allowing them to detect a wider range of frequencies and pinpoint the direction of sounds more accurately. This improvement was particularly crucial for both predators and prey, enhancing their survival skills in diverse ecosystems. The sense of smell became increasingly important for many dinosaur species. Olfactory bulbs in the brain grew larger over time, indicating a greater reliance on scent for finding food, detecting danger, and even communicating with other members of their species. Some dinosaurs, such as the duck-billed hadrosaurs, developed elaborate nasal passages that may have enhanced their sense of smell and potentially served other functions like vocalization or temperature regulation. Dinosaurs, like all living creatures, were susceptible to various diseases and ailments. Paleontologists have uncovered evidence of several health issues that plagued these ancient reptiles. One common affliction was arthritis, which left telltale signs in fossilized bones. Researchers have found dinosaur vertebrae fused together, indicating severe cases of spinal arthritis that would have caused pain and limited mobility. Infections were another significant health concern for dinosaurs. Fossil records show evidence of osteomyelitis, a type of bone infection that can cause severe inflammation and bone deformities. This condition likely resulted from injuries or wounds that became infected, potentially leading to long-term health problems or even death for affected individuals. Parasitic infections also troubled dinosaurs. Tiny holes found in some fossilized bones suggest the presence of parasites that burrowed into the dinosaurs' skeletons. These parasites could have weakened their hosts and made them more susceptible to other diseases or predation. Additionally, scientists have discovered fossilized feces containing eggs of intestinal parasites, indicating that dinosaurs suffered from internal parasitic infestations as well. Cancer, though rare in the fossil record, has been identified in some dinosaur remains. A notable example is a case of osteosarcoma, a type of bone cancer found in a Centrosaurus fossil. This discovery suggests that even these mighty creatures were not immune to the cellular mutations that can lead to cancerous growths. While our understanding of dinosaur diseases is limited by the fossil evidence available, these findings provide fascinating insights into the health challenges faced by these prehistoric animals. Paleontologists use various techniques to identify injuries in dinosaur fossils, combining careful observation with advanced technology. One key method involves closely examining the bones for any signs of abnormal growth, breaks, or unusual patterns. Healed fractures often leave distinctive marks on bones, showing where the injury occurred and how it mended over time. Computed tomography, commonly known as CT scanning, has revolutionized the study of dinosaur injuries. This technology allows scientists to peer inside fossilized bones without damaging them, revealing internal structures and potential signs of trauma or disease. By creating detailed three-dimensional images, researchers can identify subtle changes in bone density or structure that might indicate past injuries. Comparisons with modern animals also play a crucial role in understanding dinosaur injuries. By studying how bones heal in living creatures, paleontologists can make informed interpretations about similar patterns found in fossil remains. This approach helps scientists distinguish between injuries that occurred during the dinosaur's life and damage that happened after death during the fossilization process. Microscopic analysis of bone tissue provides another valuable tool for identifying injuries. By examining thin sections of fossilized bone under a microscope, researchers can detect changes in bone cell structure and growth patterns that may indicate past trauma or disease. This level of detail allows scientists to piece together a more complete picture of a dinosaur's life history, including the injuries it survived and how they might have affected its behavior and survival. Fossil records provide fascinating insights into dinosaur healing and recovery. Paleontologists have uncovered numerous examples of healed injuries in dinosaur bones, offering a glimpse into the resilience of these ancient creatures. One notable case is that of an Allosaurus, a large carnivorous dinosaur from the late Jurassic period. Its fossil shows a rib that had been broken and then healed, indicating that the animal survived a significant injury and lived long enough for the bone to mend. Another remarkable piece of evidence comes from a Tyrannosaurus rex specimen nicknamed Sue. This famous fossil displays several healed injuries, including a damaged shoulder blade and ribs that had mended after being broken. These findings suggest that even apex predators could recover from severe wounds and continue to thrive in their harsh environments. Herbivorous dinosaurs also demonstrate evidence of healing. Fossils of Triceratops, the three-horned dinosaur, have been found with healed fractures in their frilled skulls. These injuries likely resulted from intraspecies combat, similar to how modern horned animals clash today. The fact that these wounds healed indicates that Triceratops could survive and recover from intense battles with their own kind. Perhaps most intriguing are the fossils showing signs of diseases that the dinosaurs lived with for extended periods. For instance, some hadrosaur vertebrae exhibit evidence of a condition similar to modern-day arthritis. The bones show signs of this chronic condition, yet the animal clearly survived long enough for the changes to become visible in its fossilized remains, showcasing the ability of dinosaurs to adapt and persist despite ongoing health challenges. Parasites played a significant role in shaping dinosaur populations, much as they do with modern animals. These ancient creatures were not immune to the effects of parasitic organisms, which ranged from microscopic pathogens to larger parasitic worms. Fossil evidence has revealed traces of parasitic infections in dinosaur remains, offering insights into the complex ecological relationships of the Mesozoic era. One notable example comes from fossilized dinosaur feces, or coprolites, which have been found to contain eggs from parasitic worms. These findings suggest that intestinal parasites were common among dinosaurs, potentially affecting their health, behavior, and overall population dynamics. Such infections could have led to reduced nutrient absorption, weakened immune systems, and decreased reproductive success in affected individuals. Parasites might have also influenced dinosaur evolution by acting as a selective pressure. Dinosaurs with stronger immune systems or behaviors that helped avoid parasite exposure would have had a survival advantage. This could have driven the development of various defensive adaptations and behaviors over millions of years. Furthermore, parasites likely played a role in regulating dinosaur populations. By weakening or killing some individuals, particularly those already stressed by other factors like food scarcity or environmental changes, parasites could have helped maintain a balance in dinosaur ecosystems. This interplay between host and parasite was undoubtedly a crucial factor in the complex web of life during the age of dinosaurs. Bone abnormalities in dinosaur fossils provide paleontologists with valuable insights into the health and lives of these ancient creatures. These irregularities can reveal a wealth of information about injuries, diseases, and even the dinosaurs' behavior and environment. Fractures and breaks in fossilized bones can indicate traumatic injuries, possibly from fights with other dinosaurs or accidents. Healed fractures suggest that the dinosaur survived the injury, demonstrating their resilience and ability to recover. Unhealed breaks might indicate fatal injuries or provide clues about the circumstances of the dinosaur's death. Arthritis and joint diseases are also visible in dinosaur bones, showing that these animals suffered from some of the same ailments as modern creatures. Abnormal bone growths or fusions can point to infections or chronic conditions that affected the dinosaur during its lifetime. These findings help scientists understand the challenges dinosaurs faced and how they adapted to their environments. Studying bone abnormalities also allows researchers to make inferences about dinosaur behavior and social structures. For example, a high incidence of healed injuries in certain species might suggest aggressive behavior or frequent conflicts. By examining these ancient remains, scientists can piece together a more complete picture of dinosaur health, life, and the prehistoric world they inhabited. Dinosaurs' immune systems likely functioned similarly to those of modern reptiles and birds, their closest living relatives. These ancient creatures would have had both innate and adaptive immune responses to protect against pathogens and diseases. The innate immune system, the first line of defense, would have included physical barriers like tough, scaly skin and mucous membranes. Inside their bodies, white blood cells called phagocytes would have engulfed and destroyed foreign invaders. Dinosaurs also likely possessed antimicrobial proteins and a complement system to identify and neutralize threats. Their adaptive immune system would have produced specialized cells and antibodies to combat specific pathogens. This system would have improved with each exposure, creating a more robust defense against recurring infections. Evidence from fossilized dinosaur bones suggests they suffered from various ailments, including bacterial infections and parasites, indicating their immune systems were actively fighting off diseases. Interestingly, some scientists speculate that dinosaurs might have had particularly efficient immune systems. This theory is based on their long lifespans and the harsh environments they inhabited, which would have required strong defenses against a wide range of pathogens. Predatory dinosaurs faced numerous hazards in their daily lives, leading to a variety of injuries that we can observe in the fossil record. One common injury among these ancient hunters was broken bones, particularly in the ribs and limbs. These fractures often occurred during fierce battles with prey or rival dinosaurs, showcasing the intense physical demands of their predatory lifestyle. Tooth marks on bones provide evidence of violent encounters, indicating that even apex predators were not immune to attacks from their own kind or other formidable creatures. Some fossils reveal healed injuries, demonstrating that these resilient animals could survive and recover from severe wounds. Paleontologists have discovered tyrannosaur fossils with bite marks that match the teeth of other tyrannosaurs, suggesting intense competition or possibly even cannibalism within the species. Stress fractures in foot bones were another frequent injury among predatory dinosaurs. These small cracks resulted from the repeated impacts of running and pouncing on prey, much like stress fractures seen in modern athletes. The wear and tear on teeth was also common, with some predators showing evidence of broken or heavily worn teeth from years of biting into tough prey and crunching bones. Infections were a significant risk for predatory dinosaurs, often arising from open wounds sustained during hunts or fights. Fossils have revealed evidence of osteomyelitis, a severe bone infection that could be debilitating or even fatal. Despite these dangers, many predatory dinosaurs displayed remarkable ability to heal and adapt, continuing to thrive in their roles as fearsome hunters in the ancient world. Disease could have played a significant role in the extinction of dinosaurs, working alongside other factors to hasten their demise. While the prevailing theory focuses on the impact of a massive asteroid, scientists have proposed that widespread illnesses might have weakened dinosaur populations, making them more vulnerable to environmental changes. Paleontologists have discovered evidence of various diseases in fossilized dinosaur remains, including bacterial infections, parasitic infestations, and even cancerous growths. These findings suggest that dinosaurs were susceptible to a range of health issues, much like modern animals. As dinosaur populations became more stressed due to changing climates and reduced food sources, their immune systems may have weakened, allowing diseases to spread more rapidly. One intriguing hypothesis suggests that insects, particularly mosquitoes, might have transmitted diseases between different dinosaur species. This could have led to the rapid spread of pathogens across diverse populations, potentially causing widespread illness and death. Additionally, as ecosystems changed and dinosaurs were forced into closer proximity with one another, the transmission of diseases could have accelerated further. While disease alone is unlikely to have caused the extinction of all dinosaur species, it may have been a contributing factor that worked in conjunction with other environmental stressors. The combination of disease, climate change, and the aftermath of the asteroid impact could have created a perfect storm of conditions that ultimately led to the downfall of these magnificent creatures. Coprolites, the fossilized feces of ancient animals including dinosaurs, offer a fascinating window into prehistoric life. These petrified droppings provide valuable insights into dinosaur diets, habitats, and even their health. When it comes to parasites, coprolites are particularly revealing. By examining coprolites, scientists can identify the eggs and remains of parasites that once inhabited dinosaur digestive tracts. These microscopic clues paint a picture of the complex ecosystems that existed within dinosaur bodies. Researchers have discovered evidence of various parasites, including ancient relatives of tapeworms, flukes, and roundworms, some of which still plague modern animals today. The study of coprolites has revealed that some dinosaurs suffered from parasitic infections similar to those found in contemporary wildlife. For instance, scientists have identified pinworm eggs in Tyrannosaur coprolites, suggesting these fearsome predators were not immune to intestinal discomfort. Such findings help us understand the health challenges dinosaurs faced and how parasites have evolved over millions of years. Moreover, coprolite analysis allows researchers to trace the long history of host-parasite relationships. By comparing parasites found in dinosaur coprolites to those in modern animals, scientists can track how these organisms have adapted and co-evolved with their hosts over vast spans of time. This knowledge not only enriches our understanding of dinosaur biology, but also provides valuable context for studying parasite evolution and ecology in the present day. Scientists study the paleopathology of dinosaurs through careful examination of fossilized bones and other preserved remains. This field combines paleontology with medical knowledge to understand the diseases, injuries, and health conditions that affected these ancient creatures millions of years ago. One key method involves analyzing bone abnormalities. Researchers look for signs of fractures, infections, and tumors in fossilized dinosaur bones. These abnormalities can provide insights into the challenges dinosaurs faced in their environments and how they coped with injuries or illnesses. For example, healed fractures might indicate a dinosaur survived a traumatic injury, while evidence of bone cancer could shed light on the types of diseases that affected these prehistoric animals. Advanced imaging techniques play a crucial role in this research. Computed tomography scans allow scientists to peer inside fossilized bones without damaging them, revealing internal structures and abnormalities that might not be visible on the surface. These scans can help identify areas of bone growth or decay, providing clues about the health and life experiences of individual dinosaurs. Comparisons with modern animals also inform dinosaur paleopathology. By studying similar conditions in living reptiles and birds, which are the closest living relatives of dinosaurs, researchers can make informed inferences about the diseases and injuries that might have affected their ancient counterparts. This approach helps bridge the gap between the distant past and our current understanding of animal health and disease. Recent dinosaur discoveries have revolutionized our understanding of these ancient creatures. In Argentina, paleontologists unearthed fossils of a new species of Titanosaur, possibly the largest land animal to ever walk the earth. This colossal herbivore, named Patagotitan majorum, stretched over 120 feet long and weighed as much as 70 tons. Another exciting find comes from amber deposits in Myanmar, where scientists discovered the tail feathers of a small carnivorous dinosaur perfectly preserved. This remarkable specimen provides direct evidence of feathered dinosaurs and offers invaluable insights into the evolution of birds. In China, researchers uncovered a nest of dinosaur eggs with embryos inside, allowing an unprecedented look at dinosaur development. These fossilized embryos belong to a species of long-necked dinosaur and show how these creatures grew before hatching. Lastly, a recent discovery in Morocco revealed the first known aquatic dinosaur, Spinosaurus aegyptiacus. Fossil evidence suggests this massive predator had dense bones and a fin-like tail, indicating it was well adapted for life in the water. These findings continue to reshape our image of dinosaurs and their diverse adaptations. DNA research has revolutionized our understanding of dinosaurs, opening up new avenues for exploring their evolutionary history and relationships. While extracting DNA directly from dinosaur fossils remains challenging due to its degradation over millions of years, scientists have made significant progress by studying the genetic material of living descendants and close relatives. By analyzing the DNA of modern birds, which are considered living dinosaurs, researchers have gained insights into the genetic makeup of their ancient ancestors. This approach has helped clarify the evolutionary connections between different dinosaur species and has even allowed scientists to make educated guesses about certain dinosaur traits such as coloration and feather patterns. Furthermore, DNA studies have shed light on the extinction event that wiped out most dinosaurs 66 million years ago. By examining the genetic diversity of surviving lineages, scientists have been able to estimate population sizes and track how different groups of animals responded to the catastrophic changes in their environment. Recent advancements in molecular clock techniques, which use DNA to estimate when species diverged from common ancestors, have also helped refine the dinosaur family tree. This has led to a better understanding of when certain dinosaur groups emerged and how they spread across the globe. While DNA research cannot provide a complete picture of dinosaur biology, it continues to be a valuable tool in piecing together the puzzle of these fascinating creatures that ruled the Earth for over 160 million years. Computer modeling has revolutionized dinosaur research, allowing paleontologists to explore aspects of dinosaur biology and behavior that were previously inaccessible. These advanced digital tools enable scientists to reconstruct extinct species with unprecedented detail and accuracy. One key application is biomechanical analysis. Researchers use computer models to simulate how dinosaurs moved, testing hypotheses about their speed, agility, and physical capabilities. By inputting data from fossil remains into these models, scientists can estimate muscle strength, joint flexibility, and even simulate dinosaur gaits. Another crucial role of computer modeling is in studying dinosaur anatomy. Three-dimensional scans of fossils can be used to create detailed digital models of dinosaur skeletons. These models allow researchers to examine internal structures, estimate body mass, and even reconstruct soft tissues that rarely fossilize. This technology has been particularly valuable in understanding the evolution of avian dinosaurs into modern birds. Computer simulations also help paleontologists understand dinosaur ecosystems and behavior. By modeling ancient environments and the creatures within them, researchers can test theories about dinosaur social structures, hunting strategies, and responses to environmental changes. These models provide a window into the distant past, helping us better understand the lives of these fascinating creatures that roamed the Earth millions of years ago. Reconstructing dinosaur muscles and soft tissues is a fascinating process that combines multiple scientific disciplines. Paleontologists use a variety of techniques to piece together what dinosaurs might have looked like in life, beyond just their skeletal structure. One key method is comparative anatomy. Scientists study the muscle attachments and bone structures of modern animals, especially birds and crocodiles, which are the closest living relatives of dinosaurs. By examining where muscles attach to bones in these contemporary creatures, researchers can make educated guesses about where similar muscles might have attached in dinosaurs. Another important tool is computer modeling. Advanced software allows scientists to create three-dimensional models of dinosaur skeletons and simulate how they might have moved. These models can help determine the size and shape of muscles needed for various motions, providing insights into the soft tissue structure of extinct species. Rare fossil finds that preserve impressions of skin, scales, or even muscles also provide valuable clues. While such fossils are uncommon, they offer direct evidence of soft tissue structures in certain dinosaur species. This information can then be extrapolated to related species, helping to build a more complete picture of dinosaur anatomy across different groups. Paleontology is experiencing a technological renaissance, with cutting-edge tools transforming how scientists study ancient life. Advanced imaging techniques like computed tomography scans allow researchers to peer inside fossils without damaging them, revealing intricate internal structures and even preserved soft tissues. This non-destructive approach provides unprecedented insights into the anatomy and lifestyles of long-extinct creatures. Three-dimensional printing has become a game-changer in fossil research and education. Scientists can now create exact replicas of rare specimens, enabling wider access to these valuable resources. These printed models also allow for hands-on examination and manipulation, aiding in the study of biomechanics and evolutionary adaptations. Artificial intelligence and machine learning are revolutionizing the analysis of fossil data. These powerful tools can process vast amounts of information, identifying patterns and relationships that might elude human researchers. They assist in everything from reconstructing ancient ecosystems to predicting the locations of promising fossil sites. Genomic technologies are pushing the boundaries of what we can learn from ancient remains. While extracting DNA from dinosaurs remains in the realm of science fiction, researchers have successfully recovered genetic material from much younger fossils. This ancient DNA provides direct evidence of evolutionary relationships and past biodiversity, offering a window into extinct species and their adaptations to changing environments. International collaborations play a crucial role in advancing dinosaur research by bringing together diverse expertise and resources from around the world. Paleontologists, geologists, and other scientists from different countries combine their knowledge and skills to tackle complex questions about dinosaur biology, evolution, and extinction. These collaborations often lead to groundbreaking discoveries by pooling data from various fossil sites across continents. For example, comparing dinosaur fossils found in North America with those unearthed in Asia or South America helps researchers understand how these ancient creatures migrated and evolved over time. This global perspective is essential for piecing together the puzzle of dinosaur distribution and diversity throughout Earth's history. International teams also benefit from shared access to advanced technologies and specialized equipment. High-resolution computed tomography scanners, electron microscopes, and sophisticated dating techniques are not always available in every country. By working together, scientists can utilize these tools to analyze fossils in unprecedented detail, revealing new insights into dinosaur anatomy, behavior, and environmental adaptations. Furthermore, collaborative efforts often result in more comprehensive and well-funded expeditions to remote fossil sites. These joint ventures allow researchers to explore areas that might be challenging for a single institution to access, leading to the discovery of new species and expanding our understanding of prehistoric ecosystems. Through international cooperation, dinosaur research continues to uncover fascinating details about life on Earth millions of years ago. Studying dinosaur behavior presents numerous challenges for paleontologists and researchers. One major obstacle is the vast time gap between the present day and when dinosaurs roamed the Earth. This immense separation of millions of years means that direct observation is impossible, forcing scientists to rely on indirect evidence and inference. Fossilized remains, while invaluable, provide only a snapshot of an animal at the moment of death. They cannot directly reveal complex behaviors, social structures, or daily activities. Researchers must carefully examine fossil evidence, such as bone structure, tooth wear, and preserved trackways, to piece together clues about how dinosaurs might have moved, hunted, or interacted with their environment. Another significant challenge is the incomplete nature of the fossil record. Many dinosaur species are known from only fragmentary remains, making it difficult to form a comprehensive understanding of their anatomy, let alone their behavior. Soft tissues, which could provide crucial insights into muscle structure, organ placement, and even skin coloration, rarely survive the fossilization process. Environmental factors also complicate behavioral studies. The world dinosaurs inhabited was vastly different from our own, with different climates, vegetation, and geographical features. Scientists must consider these factors when interpreting fossil evidence and attempting to reconstruct dinosaur ecosystems and behaviors. Despite these challenges, ongoing research and new technologies continue to shed light on the fascinating lives of these ancient creatures. Scientists follow a specific process when naming new dinosaur species, combining careful analysis with established conventions. The naming begins after paleontologists unearth fossils that appear distinct from known species. They meticulously study the bones, comparing them to existing records and specimens to confirm the discovery is indeed novel. The scientific name given to a new dinosaur species consists of two parts: the genus and the species. The genus name often describes a notable characteristic or pays homage to a person or place. The species name further distinguishes the dinosaur, perhaps noting a unique feature or honoring a significant individual. Paleontologists must adhere to the International Code of Zoological Nomenclature when proposing new names. This ensures consistency across the scientific community. They publish their findings in peer-reviewed journals, presenting evidence for the new species and justifying the chosen name. Naming a dinosaur is a significant responsibility. The chosen name becomes part of scientific literature and popular culture, potentially inspiring future generations of paleontologists and dinosaur enthusiasts. As new discoveries continue to emerge, this naming process helps organize our ever-expanding knowledge of prehistoric life. Stable isotope analysis has revolutionized our understanding of dinosaur ecology, offering unprecedented insights into the diets, habitats, and behaviors of these ancient creatures. This powerful scientific technique examines the ratios of different isotopes in fossilized tissues, such as bones and teeth, providing a window into the lives of dinosaurs that lived millions of years ago. By analyzing carbon isotopes in dinosaur remains, scientists can determine whether a species was primarily herbivorous or carnivorous, and even identify specific types of plants they consumed. Oxygen isotope ratios offer clues about the climate and water sources dinosaurs relied on, helping researchers reconstruct ancient environments and migration patterns. Nitrogen isotope analysis reveals information about an animal's position in the food chain, distinguishing between predators and prey. This technique has challenged long-held assumptions about certain dinosaur species, revealing that some presumed carnivores may have had more varied diets than previously thought. Strontium isotopes in fossilized teeth can trace dinosaur movements, showing whether individuals roamed vast territories or stayed in localized areas. This information provides valuable insights into dinosaur behavior and social structures, painting a more complete picture of how these fascinating creatures lived and interacted with their environments millions of years ago. Our understanding of dinosaur physiology has undergone significant changes in recent years, challenging long-held assumptions and revealing new insights into these ancient creatures. One major shift has been the recognition that many dinosaurs were likely warm-blooded, similar to modern birds and mammals, rather than cold-blooded like reptiles. This revelation came from studying the microscopic structure of dinosaur bones, which showed growth patterns indicative of high metabolic rates. Another important development has been the discovery of feathers on a wide variety of dinosaur species, not just those closely related to birds. This finding has revolutionized our image of dinosaurs, transforming them from scaly, reptilian beasts to often colorful, feathered creatures. Advanced imaging techniques have even allowed scientists to determine the colors of some dinosaur feathers, providing a more vivid picture of how these animals may have appeared. Recent research has also shed light on dinosaur locomotion and posture. We now know that many large dinosaurs, such as Tyrannosaurus rex, likely moved more slowly and deliberately than previously thought, based on biomechanical studies and computer simulations. Additionally, evidence suggests that some herbivorous dinosaurs may have been more agile and capable of faster movement than once believed. Lastly, new fossil discoveries have expanded our knowledge of dinosaur sensory capabilities. For instance, studies of well-preserved skull fossils have revealed that some dinosaurs had keen senses of smell and hearing, while others may have had enhanced visual abilities. These findings continue to refine our understanding of how dinosaurs interacted with their environment and each other, painting a more complex and nuanced picture of dinosaur physiology and behavior.